The Moon, our only satellite. Barren and void of oxygen and life. Where temperatures on its surface range from a blistering 230 degrees Fahrenheit to a frozen minus 290 degrees at night. Here, there is no weather, no wind. It is serene, still, unchanged for millions of years. Beyond it, the Earth. Surrounded by a thin gaseous layer, its surface often remains hidden beneath the ever-changing veil of clouds. This layer of gases protects the Earth from harmful solar radiation, limits the temperature extremes, and contains the weather that scars and molds the features of its surface. On Earth, there is never such a thing as no weather, and the rate at which our atmospheric conditions change can be dramatic. As pilots, we must become attuned to the atmosphere and the weather it contains. Since the air is our medium of movement, understanding weather phenomena and the forces behind them are important considerations. The atmosphere that surrounds the Earth is relatively thin. Although it extends several 100,000 feet into space, about half of the total atmosphere is compressed below 3.5 miles. Many people have the false impression that the atmosphere is mostly comprised of oxygen, but in reality, only 21% of the total gas is oxygen. Nitrogen makes up most of our atmosphere, with carbon dioxide, argon, and other gases making up the remaining 1%. The atmosphere is made up of several basic layers, with the lowest layer being the troposphere. This layer slopes upward from about 20,000 feet at the poles to about 60,000 feet at the equator. Most of the weather which you will be concerned with will be found within this layer. Above the troposphere is a thin layer known as the tropopause, which acts as a lid on the troposphere, keeping most of the moisture within the layer below. The stratosphere extends to about 22 miles above the surface. The air within this layer is very dry and stable. Few cloud formations penetrate into this layer. Above the stratosphere are the mesosphere and the thermosphere. These layers have very little effect on the weather. The gases in the atmosphere contain molecules that are constantly in motion. As the air is heated, these molecules speed up, creating more space between them. The result is fewer molecules per given volume of air. When the air is cooled, the molecules become less active, meaning more can exist in a given volume of air. This cooler air is heavier and denser than the warmer air. The differences in air density are the basis for the movement and circulation of the atmosphere. To demonstrate this principle, suppose we have two rooms, one which contains cold, dense air, while the other has warmer, lighter air. When the door is opened, the air begins to mix. The heavier, colder air slides under the warmer air, creating a cold draft on the floor. As the cold air fills the bottom of the room, the warmer air replaces the colder air. On a larger scale, the draft created between the rooms is called wind. Air replacement due to these density changes drives our major weather systems. This density difference is due to the pattern of global heating. At the equator, light from the sun strikes the surface at an almost perpendicular angle. Near the poles, the surface of the Earth is largely turned sideways to the sun. This results in more atmosphere between the sun and the Earth at the poles. This greater amount of atmosphere cuts down the intensity of the sun's rays. Also, the same amount of light that would cover a given area on the equator is distributed over a far larger area at the poles. The result is less heating energy per square mile. As the sun's radiation heats the tropical areas of the Earth, the air becomes less dense and rises. Because less dense air does not exert as much pressure, a permanent low-pressure area forms near the equator. Nearing the top of the troposphere, the warm air is displaced sideways, away from the equator. The air continues northward and southward, slowly becoming cooler until it begins to descend near the poles. This colder descending air creates a permanent high-pressure area near the poles. The air then returns along the surface, back toward the equatorial areas, to replace the rising air. If the Earth didn't rotate, there would be a continuous circulation pattern from the polar highs to the equatorial low. But because it does, this theoretical one-cell circulation pattern becomes a three-cell pattern. In this circulation pattern, the air near the equator still rises and flows toward the pole. But this branch, known as the Hadley cell, only reaches about 30 degrees north. Here it combines with sinking air from the Ferrel cell that corresponds with a semi-permanent subtropical high-pressure area. Near 60 degrees north, the warm surface winds of the Ferrel cell and the cold winds of the polar cell collide, rising to produce an area of low pressure. In addition, these airflow patterns are affected by Coriolis force. In order to better explain how Coriolis works, let's use the example of two ball players attempting to play catch on a merry-go-round. As the pitcher throws the ball, it travels in a straight line, but not to the catcher. To the thrower's perspective, some force seems to be turning the ball to the right. This same situation applies to air as it flows from the North Pole to the equator. Because of the Earth's rotation, the wind seems to be deflected to the right. This apparent rotation is called Coriolis force. Atmospheric pressure, or the concentration of air molecules over a given area, is measured in terms of inches of mercury, or millibars. 1 inch of mercury is equivalent to approximately 34 millibars. The measurement of pressure is done with the use of a barometer. This instrument is nothing more than a partial vacuum within a glass tube containing mercury. As the pressure of the air exerts a force on the container of mercury, the mercury will rise. The average atmospheric pressure of the Earth will make the mercury rise 1,013.2 millibars, or 29.92 inches. This measurement is considered to be standard pressure. During periods of higher atmospheric pressure, the force exerted upon the mercury is greater, which forces the mercury to rise. The reverse happens during periods of lower than standard pressure. If we imagine standard air pressure as a plane, we can visualize the relationship between air masses with different densities. On the left is a high-pressure system, or a mass of denser than standard air. It is more dense at the center of the mass. On the right is a low-pressure system, or a mass of less dense air. Pressure changes occur more rapidly directly between the center of the high and the center of the low. As we rotate the image to a top view, we can draw lines around the areas that appear to have the same height, or in this case, the same amount of atmospheric pressure. These lines are called isobars, and they are drawn on weather maps to represent areas of equal pressure. By using these lines, you can determine the position of high and low pressure areas. You can also tell how large or severe they are by the number of lines and how they are placed. Notice how the isobars are closest together directly between the high and the low. The closer the lines, the stronger the pressure gradient. Air from a high-pressure area will flow directly toward a low with a force which relates to the pressure gradient. If the Earth didn't rotate, highs and lows would exchange wind directly in this manner. However, Coriolis force from the rotation of the Earth is also acting on these systems. As winds spill off a high-pressure area in the northern hemisphere, they are deflected to the right. This results in a clockwise flow around a high and a counterclockwise flow around a low. As the wind is driven around these systems, the air closest to the surface is slowed by the friction of the ground. When this happens, the Coriolis force is diminished until the pressure gradient force becomes greater. The resulting wind tends to flow across the isobars toward areas of lower pressure. At altitude where airflow is not affected by the surface friction, the wind continues to flow parallel to the isobars. In addition to creating large patterns of wind around highs and lows, differences in atmospheric density can cause wind flow on a local level as well. In areas near the ocean or other large bodies of water, local changes in heating and atmospheric density can cause daily wind flow patterns. During the day, water slowly absorbs heat. On the nearby land, the sun's radiation only penetrates a few inches into the soil. The land surface heats up much quicker than the water. As the air over the land warms up and begins to rise, air over the water is being cooled down because of the cooler surface of the ocean. The cool air then flows inland to replace the rising warm air. This produces a sea breeze flowing inland from the ocean. During the night, the land cools very quickly. The air above the landmass begins to cool and sink. The ocean, now warmer than the land, begins to warm the air above it, causing the air to rise. The flow of the cycle now reverses, and in the evening, a land breeze will be experienced. Local wind patterns can also form as the result of mountainous terrain. One of these is a foehn wind, which occurs when there is a mass of cold, dense air near the top of a mountain range. As the air pushes over the top of the range, the cold air begins to descend down the other side. As this air accelerates and replaces the warmer air beneath it, it begins to compress and warm up. As the air heats, it will eventually become warmer than the air it is replacing. This causes the atmosphere at the bottom of the hill to become warmer. These winds can become very strong, with gusts exceeding 120 miles per hour. In the Rocky Mountains, they are called Chinooks. In the Sierra Nevada mountains, they are the Santa Ana winds. Regardless of their names, these winds can produce large amounts of damage and are hazardous to aircraft, both in the air and on the ground. They can occur during what would normally be perfectly good VFR weather, and is one of the reasons surface wind reports are important to you when receiving a weather briefing. We have seen how heating and the differences in air density can produce wind. The other major force in the formation of weather is moisture. Moisture occurs on our planet as a solid, a liquid, and a gas. Within these states, it can take many forms. We see moisture as clouds, as rain, hail, or as snow, ice, or water. Dew and frost are also forms of moisture. How water changes back and forth from state to state is very important to the formation of weather. We have all experienced the effects of evaporation, such as water evaporating from a lake. When water turns from a liquid to a vapor, the process requires heat. This heat energy is drawn from any available nearby source and is stored by the vapor. When the water vapor is returned to a liquid through the process of condensation, the latent heat that was stored during evaporation is now released. The heat exchange during evaporation and condensation is a major factor in the vertical movement of air columns. Thunderstorms, for example, can be developed by this force. Originally, the air begins to rise through a force such as the sun heating the surface, which in turn warms the air above it. As this warm air cools and eventually condenses, the latent heat released from condensation will, under the right conditions, continue or increase the strength of the updraft. If this process continues, a thunderstorm can develop. In vapor form, molecules of water exist between other molecules contained in the atmosphere. When the air is warm, more room exists between the molecules of air. Therefore, more water molecules can squeeze between the air molecules. When the air is colder and the air molecules are closer together, less water vapor can fit between the already close air molecules. For this reason, cold air cannot hold as much water as warmer air. Dew point is the temperature at which an air mass becomes completely saturated with water vapor. In other words, it will hold as much water as the temperature will allow. When an air mass becomes completely saturated, condensation occurs. Let's say that we have an air mass with a temperature of 55 degrees Fahrenheit. If the dew point is also 55 degrees, then the air is 100% saturated. If condensation nuclei are present, then condensation will occur. Clouds, fog, and dew are all forms of condensation. When water that is formed on the condensation nuclei becomes too heavy for the atmosphere to support, then precipitation occurs. Since the moisture content in an air mass is relatively constant, the air mass must usually undergo some form of cooling in order for condensation to occur. For example, if the air is 50% saturated at 55 degrees, then the air must be cooled to about 37 degrees in order for condensation to occur. When the temperature reaches 37 degrees, this air mass will be 100% saturated. Weather is something that we must deal with daily as pilots. It is constantly changing and infinitely complex. Knowing the basic driving and manipulating forces of our Earth's weather patterns will help you to understand the more detailed conditions and concepts that will be introduced in the following weather sections. Being able to understand the concepts of weather development will not only help you understand the current conditions, but will also help you anticipate future changes as well.
It looks like it's going to be a cold one today. An Arctic cold front moved into our area around 3 this morning and has already dropped 3 to 4 inches in some parts of the city. The air mass associated with this front is stable, and with all the moisture that's being pushed up from the Gulf, we're in for snow the rest of the day and possibly tomorrow.
Every day, all over the world, people are dealing with the effects of the weather. In the previous section, we saw how the forces of air density, Coriolis, temperature, and moisture worked independently of each other. In this section, you'll see how they interact to produce the weather phenomena we see every day. The type of weather we experience is, in part, related to whether or not air rises or falls in relation to the surrounding air. The term used to measure how much relative resistance an air mass has to this vertical movement is called stability. A stable air mass, for example, resists vertical motion. This inhibits large cloud formation, heavy precipitation, and severe weather. An unstable air mass, on the other hand, has the potential for significant cloud development, turbulence, and hazardous weather. The weather in the tropics is a good example of unstable air. With its warm temperatures and high humidity, daily thunderstorms are commonplace. Air mass stability plays a large role in the development of weather. We can best see this role in the development of clouds. There are 2 basic types of clouds, cumulus and stratus. Cumulus clouds are formed by rising currents of air, which gives them a piled up or bunched appearance. They warn of unstable air, turbulence, and showery precipitation. Visibility outside the precipitation is usually good. In air masses with a high amount of stability, stratus clouds may form. Resisting vertical movement, these clouds form in smooth layers and often extend over large distances. Since the air is stable, flight near stratus clouds is normally smooth. Precipitation from these clouds can be continuous and last for several hours or even days at a time. The visibility associated with stratus clouds is usually poor. In addition, clouds can further be grouped into high clouds, middle clouds, low clouds, and clouds with extensive vertical development. Cirrostratus, cirrocumulus, and cirrus clouds are examples of high clouds. They are composed almost entirely of ice crystals and seldom pose hazards to pilots. Most names of middle clouds contain the prefix alto, such as altostratus or altocumulus. These clouds are composed of water, ice crystals, or supercooled water, which is water that has been cooled below its freezing point but is still in a liquid state. They can contain moderate turbulence and potentially severe icing. A cloud with a name containing the prefix nimbo or the suffix nimbus contains a large quantity of moisture. A nimbostratus cloud, for example, can produce widespread areas of snow or rain. While classified as a middle cloud, the nimbostratus cloud can merge into the clouds formed at low altitudes. A cloud which can be very deceptive to pilots is the lenticular cloud. This lens-shaped cloud may form over mountain crests during high wind conditions. Even though it looks smooth and serene, it is, in reality, a good indication of heavy turbulence and should be avoided. The low clouds form near the surface and extend to around 6,500 feet. Clouds within this group include the stratus, stratocumulus, and fair weather cumulus clouds. The thunderstorm, or cumulonimbus cloud, is an example of a cloud with extensive vertical development. This type of cloud can have its base as low as 1,000 feet and extend up to the heights associated with high clouds. Flight near a thunderstorm can be extremely dangerous. These hazards will be discussed in the next section. So far, we have talked about the stability of an air mass and the types of clouds which can form if the air mass is stable or unstable. But how and where do these air masses begin, and what happens to them as they move? As we discussed earlier, the global circulation patterns form high and low pressure areas. The high pressure areas, located at the poles and in the tropical areas, act as source regions for air masses. If an air mass forms over water, it is further classified as maritime. This type of air mass will usually contain more moisture than a continental air mass, which forms over the land. As an air mass leaves its source region, it is modified. The amount of modification depends on the speed of the air mass, the nature of the region over which it is traveling, and the difference in temperature between the air mass and the region. As an air mass moves, it comes in contact with other air masses of different properties. Since air masses with different temperatures and pressures do not mix very well, their boundary forms a front. As you fly across a front, you may experience discontinuities, which are rapid changes in atmospheric conditions. These include temperature, wind, and pressure. Temperature is probably the most easily noticed change, but the two which should concern you more are wind and pressure. An undetected change in the wind could cause you to drift off course inadvertently. When flying through a front, you should expect a wind shift and adjust your navigation accordingly. Since there is usually a pressure change when you cross a front, you should reset your altimeter to the correct setting to avoid being higher or lower than the indicated altitude. Fronts are defined by the type of air mass that is in the overtaking position. In other words, if a colder air mass is overtaking a warmer one, then the resulting front is called a cold front. This definition is relative, though, because a cold front can be any temperature, as long as it is cooler than the air mass it is overtaking. As a cold front moves, it replaces warmer air at the surface. Since colder air is denser, it pushes the warmer air aloft. If this warmer air is relatively dry and stable, stratiform clouds form in the vicinity of the advancing cold front. If the warmer air is relatively moist and unstable, cumuliform clouds may form along the front. A rapidly moving cold front can create thunderstorms many miles ahead of the frontal boundary. A line of these thunderstorms parallel to the front is called a squall line and can contain violent weather. The thunderstorms in a squall line can grow to 65,000 feet and can be especially violent. These storms often produce heavy rain, large hail, and even tornadoes. In contrast to a fast-moving front, the slope of a slow-moving cold front is not as steep and the lifting action is not as great. Therefore, the weather is less severe. When a warmer air mass overtakes a colder one, a warm front exists. Because of the difference in relative densities, the warm air will slowly slide over the colder air. This can result in very little vertical air movement. If enough moisture is present and the colder air mass is relatively stable, stratiform clouds usually form. These clouds may extend for many miles ahead of the front. However, there may be some cumulus clouds present in the form of embedded thunderstorms if unstable air is present. The weather associated with a warm front usually includes low ceilings, fog, and a subsequent reduction in visibility. When two air masses of relatively equal strength collide, a stationary front may form. Here, there is very little movement. The weather associated with this front can vary depending upon the temperature, moisture content, and stability of the air masses. It is usually a mixture of that found with both warm and cold fronts. One of the most complicated frontal systems is the occluded front. In this case, a fast-moving cold front is overtaking a slower-moving warm front. There are two types of occluded fronts. The one shown here is a warm front occlusion because the air ahead of the warm front is colder than the overtaking cool air mass. Of the two types of occlusions, this one produces the more severe weather. The other type is a cold front occlusion. Here, the cold air is replacing cool air at the surface. This type of occlusion generally doesn't produce weather as poor as a warm front occlusion. However, like the warm front occlusion, the weather associated with it is hard to predict and can produce a wide variety of weather considered dangerous to most general aviation aircraft. With weather patterns constantly changing, it is important to understand the factors behind their development and to get a good pre-flight weather briefing before flying. In the next section, we'll take a look at how these weather systems can be hazardous to flying and what you can do to predict these conditions and avoid them. Weather hazards come in many forms. Some are clearly visible, while others may be encountered unexpectedly. In this section, we'll look at some of the common hazards and discuss how you can avoid them. The thunderstorm is a weather phenomenon which is capable of producing very violent conditions. Thunderstorms can develop rapidly, and the hazards associated with them can exist for several miles beyond the storm itself. Three atmospheric conditions are necessary for their formation. The first is unstable air, which allows for extensive vertical development. Second, there must be some type of lifting force, such as convection. Finally, moisture must be present. A thunderstorm passes through three stages: cumulus, mature, and dissipating. The cumulus stage is characterized by updrafts, which may extend from near the Earth's surface to several thousand feet above the visible cloud. Also, during this stage, water droplets form into raindrops. However, instead of falling to the Earth as precipitation, they are suspended in the cloud by the updrafts. The second, or mature stage, begins as the raindrops begin to fall to Earth. You can expect the most violent weather to occur during this phase. At this time, the raindrops have grown so large that the updrafts can no longer support them. As they fall, they pull air with them, creating downdrafts, which may exceed 2,500 feet per minute. As the downdrafts reach the surface, they spread out, creating strong, gusty surface winds. The dissipating stage begins when the cell becomes predominantly downdrafts. During this stage, the intensity of the precipitation decreases. It is also during this stage that the upper-level winds often blow the top of the cloud downwind, giving it an anvil appearance. However, this does not necessarily mean that the storm is over. Severe weather could continue well after the anvil forms. While thunderstorms usually have similar physical features, they can differ in intensity, degree of development, and associated weather. Lightning is one of the weather hazards that always accompanies thunderstorms. Other hazards might include heavy rain, hail, turbulence and gusty surface winds, and even tornadoes. As you gain experience, you'll learn how weather limits your flying. But regardless of your experience, you should always avoid intentionally flying into or near thunderstorms. To do this, you must know where they exist or are likely to develop. You can determine this by checking weather reports and forecasts prior to departure and during your flight. If widespread thunderstorms are being reported, you might find it necessary to delay or cancel your flight. If you encounter thunderstorms while airborne, you should never attempt to fly over them. These clouds can build faster than your airplane is capable of climbing. Flying below the cloud can be just as hazardous because of the extreme turbulence produced by the downdrafts. And you shouldn't try to fly around a thunderstorm unless you can maintain at least 20 miles between it and yourself. If that isn't possible, it might become necessary to turn around or fly to an alternate and wait for the storm to pass. The turbulence associated with thunderstorms varies in intensity from light, annoying bumps to severe jolts that can damage your airplane and injure its occupants. To minimize its effect, slow to maneuvering speed or less. One form of turbulence, called wind shear, is a sudden shift in wind speed or direction. It can occur at any altitude and in a vertical or horizontal plane. Wind shear is often associated with a more serious phenomenon called microburst. A microburst is an intense, localized downdraft which descends from the base of a convective cloud. As the air reaches the surface, it spreads out in all directions, often forming in a circular motion. This circulation creates an area of severe horizontal and vertical wind shear. A wind shear is particularly dangerous when it's in the proximity of an airport. To show you what can happen, suppose you're taking off into a microburst. You would initially experience a headwind and an increase in performance. When the aircraft reaches the point where the wind shears to a tailwind, it experiences a severe decrease in performance which could lead to disastrous results. Some airports are equipped with a low-leveled wind shear alert system, which allows controllers to advise you of significant wind differences on the field. Whether or not this system is available, any time a thunderstorm is in the vicinity, you should anticipate the presence of a microburst. While most microbursts are associated with heavy precipitation, moisture does not have to be present. They sometimes occur in virga, or streamers of precipitation that trail behind clouds and evaporate before reaching the ground. If there is no precipitation, a ring of dust on the ground, or trees being blown in different directions may be your only indications. Do not take off or land at an airport when you suspect a microburst exists. If you are in the air, delay your landing or divert to another airport. Most microbursts will pass over an area within a few minutes. Another form of turbulence occurs near mountains. It develops when the air is stable and winds in excess of 40 knots are flowing horizontally over mountain ridges. However, some turbulence may develop when the winds blowing over the ridges exceed 25 knots. If the air is unstable, the air on the windward side of the ridge will probably be extremely turbulent. If there is enough moisture present, cumulus clouds and possibly thunderstorms may develop. As the wind crosses the ridge, it spills down the leeward side. This may create violent downdrafts which could exceed the climb capability of your aircraft. If the air is stable, the wind flow will be smooth on the windward side. As it crosses the mountain, it tends to flow in layers or waves. The crests of these waves are often marked by lens-shaped clouds. These clouds are called standing lenticulars because they form in the updrafts and dissipate in the downdrafts, giving them an appearance of remaining stationary. Anytime this type of cloud is present, you should expect turbulent conditions. If you fly at airports used by large aircraft, you should be alert for another type of turbulence called wake turbulence. This type of turbulence occurs when a large airplane is generating lift and is most pronounced at low airspeeds and high angles of attack, such as when taking off or landing. Although it eventually dissipates, wake turbulence can persist for several minutes. If you encounter it as you're attempting to take off or land, the results could be disastrous. At controlled airports, controllers are required to provide minimum separation between small and large aircraft. However, you have the responsibility for avoiding wake turbulence. To ensure that you don't encounter wake turbulence while landing behind a large departing aircraft, you should touch down well before the airplane's rotation point. When making an approach behind a large aircraft that has just landed, stay above its glide path and touch down beyond its touchdown point. When departing behind a large aircraft that has just taken off, you should lift off before the airplane's rotation point and remain above its flight path. If a light crosswind is present, you should fly upwind of the large aircraft's flight path. And finally, if you're departing after a large aircraft has landed, make sure you lift off at a point beyond the touchdown point. Another weather hazard you should be familiar with is structural icing. Since it occurs only in visible moisture when the aircraft's surface is at or below freezing, you're unlikely to encounter structural icing until you're instrument rated. The major reason icing is dangerous is because it changes the shape of the airfoil and destroys its lift. It can also increase the weight of the airplane and restrict control movements. Frost is a related element that you are more likely to encounter as a VFR pilot. Like icing, it can be hazardous because it interferes with the smooth airflow over the wings, resulting in a loss of lift. You should never take off unless you have removed all frost and other ice formation. As a VFR pilot, virtually all of your flying will be done with reference to the ground. When your visibility is restricted by elements such as haze, smog, smoke, fog, blowing dust, snow, or volcanic smoke and ash, you may have problems determining your position. Fog is one of the most persistent weather hazards and is frequently the cause of surface visibilities being less than 3 miles. It can form rapidly, changing from VFR to IFR conditions in just a few minutes. Anytime you have high humidity, a small temperature dew point spread, and light surface winds, you should anticipate fog and have an alternate course of action if it does occur. Although volcanic eruptions are not a common occurrence, volcanic smoke and ash can pose an extreme flight hazard. In addition to reducing flight visibility, volcanic ash can cause compressor stalls and flameouts in jet engines. In piston-powered aircraft, it can also cause severe damage or engine failure. Ash clouds are most dangerous close to the volcano when an eruption has just occurred. This is due to the large amount of ash particles, hot gases, and dust. Because volcanic ash is highly abrasive, control surfaces can be damaged and the pitot-static system and ventilation systems may become clogged. When volcanic material is injected into a stable atmosphere, the ash and smoke may be carried long distances by atmospheric winds. The gases and smaller particles spread out and may be very difficult to distinguish from an ordinary water or ice cloud. Currently, the National Weather Service monitors volcanic eruptions through pilot reports, radar, and satellite observations. Then, by using computer forecast models, the NWS forecasts ash cloud movements and provides subsequent advisories as required. If you observe a volcanic eruption, notify ATC. However, do not jeopardize flight safety to make a report. Immediately take evasive action by turning upwind to avoid entering the ash cloud. Don't attempt to fly through or climb above the cloud. When you are safely away and you can make your report to ATC, provide the location and altitude of the cloud, wind direction, and a description of the ash cloud and eruption. As you gain experience, you'll learn to recognize hazardous weather conditions. In addition, you'll learn that with proper pre-flight planning, you can avoid areas of potentially dangerous weather before you encounter it in the air. In the next volume, we'll discuss the types of information which are available to you and how to interpret them. Many people believe predicting the future is a hazy, inexact process. For them, an accurate prediction depends on blind luck or good fortune. However, relying on luck to predict the weather for your flight is not wise. As a pilot, you must rely on good forecasts. Fortunately, a number of methods with varying accuracies have been developed to help you anticipate weather conditions. Have you left your house in the morning for work, noticed the nice weather, and determined it would still be nice later in the day? If so, you have made a persistence forecast. By assuming the existing weather conditions won't change during the day, you predict the weather in the afternoon will be as nice as it was in the morning. However, this method of forecasting is not reliable over long periods of time, usually not more than 1 or 2 hours. Trend forecasting predicts that, without interruption, a weather event, like a storm cell, will continue moving in the same direction and at the same speed it's currently moving. In this case, the storm will reach the airport in less than 2 hours if atmospheric conditions don't act to change its course and speed. Similar to persistence forecasts, trend forecasting is generally accurate for only a few hours. At times, predictions are based on the average historical weather for an area. Known as climatological forecasts, they are reliable in areas and times which enjoy little change in day-to-day conditions. For instance, San Francisco has a generally moderate climate and may receive less than 1 rainy day per month during the summer. The analog forecast also uses historical data for predictions. This method is useful in predicting the temperature for a given day. By combining past data for a certain day with prevailing weather conditions, a meteorologist can accurately predict the expected high or low temperature. One of the better ways to predict the weather is the meteorological forecast. A good meteorologist can reliably forecast out to 12 hours by using his knowledge of atmospheric processes. This type of forecast can be a valuable tool for pilots. Powerful computers and mathematical equations have increased forecast accuracy by modeling weather trends. The result is a numerical weather prediction. The computer runs one forecast model on top of another to determine their effects over time. Doing so produces a relatively accurate picture of future weather events. Regardless of the forecast you receive, you can be sure the information contained was collected and compiled with the help of numerous agencies. With thousands of land and sea-based reporting stations, large volumes of weather data can be collected and analyzed. Through the coordinated action of several agencies, including the World Meteorological Organization, National Weather Service, and numerous private organizations, weather information is disseminated for your use. Although the weather collection and dissemination network is extensive and thorough, it's not perfect. While forecasting accuracy continues to improve, long-term forecasts and short-term predictions of localized weather phenomena are still difficult to develop with reliability. Even though forecasters aren't always precise, the experience and skill they can provide you is superior to other methods of predicting the future. After all, when it comes to aviation weather, having the edge provided by a good forecast is better than taking your chances.
A weather check is not only an important part of your pre-flight planning, but is required for any flight not in the vicinity of an airport. A wide variety of weather reports and forecasts are available for pilots to use. Today, there are several ways you can access these reports and forecasts, including a personal visit to any flight service station, computer-based weather briefings, and weather reports by fax. Since the systems allow direct access to printed weather information, learning to decode actual reports and forecasts is just as important as ever. During this program, you'll become familiar with aviation routine weather reports, pilot weather reports, radar reports, terminal aerodrome forecasts or TAF, area forecasts, airmets, SIGMETs, convective sigmets, winds and temperatures aloft forecasts, and finally, notices to airmen or NOTAMs. Let's begin our discussion with a look at METAR, or Aviation Routine Weather Reports, which contain the latest reported hourly weather observations for various locations. The information for each reporting station is printed in a coded format beginning with the report type. Here, the word METAR represents a routine report. If SPECI is in this location, it indicates a special, non-routine METAR weather report, which means the report was issued at other than the regular time, and there has been a significant change in the weather since the last report. The next element contains the station identifier. Notice the METAR code uses the ICAO, International Civil Aviation Organization, 4-letter station identifier. The stations within the contiguous 48 states are prefixed with a K. Here, KDEN is the identifier for Denver. Following the station identifier are the date and time in Zulu of the weather observation. When a report is generated by an automated weather observation station that has no human intervention, the word auto will follow the date-time group. If a correction is made to a report, the abbreviation COR is substituted for the word auto. The remainder of the printout is dedicated to weather, beginning with wind. Surface wind readings make up this section. The wind direction is given first, followed by the wind speed in knots. Here, the wind is blowing from 330 degrees at 18 knots. Variations of wind speed are shown as gusts and are indicated with a G. In this example, the wind is from 290 degrees at 30 knots, gusting to 45 knots. If the wind direction is variable and the velocity is 6 knots or less, it is noted by the prefix VRB. Here, the wind is variable at 4 knots. When the wind direction varies by 60 degrees or more, a variable group consisting of the extremes in wind direction, separated by a V, will follow the prevailing wind group. In this example, the wind direction has varied from 290 to 360 degrees. A calm wind condition is indicated by 5 zeros followed by KT. The next element of the METAR report gives the visibility in statute miles. At Denver, the visibility is 1/2 statute mile. When runway visual range is reported, it is preceded by an R. The next 2 digits are the runway number, followed by the visual range measured in feet. Here, the RVR for runway 31 is 2,600 feet. The next section of the METAR report is the present weather at the time of the observation. The type of precipitation or the obscuring phenomena is shown in code and may be preceded by an intensity symbol, a proximity code, and a descriptor code. Intensity levels are shown as either a plus or minus symbol and only apply to the first type of precipitation reported. This example indicates that light rain is falling. The plus symbol denotes heavy rain, and no symbol indicates moderate intensity. When the reported meteorological conditions are between 5 and 10 statute miles of the usual point of observation, the code VC is used, indicating the reported weather is in the vicinity of the airport. 2-letter descriptors are used to provide even more information about precipitation and obscuring phenomena. Here, FG indicates that fog is the predominant obscuring phenomena. Other common descriptors are TS for thunderstorms, SH for showers, FZ for freezing, DR for low drifting, MI for shallow, and BC for patches. The common letters used to indicate precipitation and obstructions to visibility include RA for rain, DZ for drizzle, GR for hail, FU for smoke, and HZ for haze. Additional codes are listed in your manual. The next block is used to report sky conditions. The amount of coverage is reported in eighths of sky cover, and is represented by different contractions. If the sky is clear, meaning there are no clouds visible to the observer, the report will contain the letters SKC. At automated stations, the abbreviation CLR is used to indicate no clouds below 12,000 feet are detected. The letters FEW in the METAR report mean up to 2/8 of the sky is covered by clouds. A scattered layer, or SCT, means that the clouds cover 3/8 through 4/8 of the sky. A heavier sky cover is referred to as broken and is indicated on the report with the letters BKN. In this case, the clouds are covering 5/8 through 7/8 of the sky. When OVC appears, the sky is reported as overcast, which means clouds completely cover the sky. When the sky is reported as broken or overcast, a ceiling is said to exist. The height of the cloud bases are reported with 3 digits measured in hundreds of feet above ground level. Here, the first layer is a scattered layer at 800 feet, with a second overcast layer at 1,000 feet. When the sky is obscured by a surface-based layer, the vertical visibility is reported. The letters VV indicate an indefinite ceiling, and the 3-digit number is the height in hundreds of feet. In this case, the vertical visibility is 400 feet. Cumulonimbus clouds or towering cumulus clouds are observed. The letters CB or TCU will follow the number representing the height of the cloud base. In this example, the observer has reported a scattered layer of towering cumulus at 1,500 feet. The next segment of the report gives the temperature and dew point in degrees Celsius. When these temperatures are below 0 degrees Celsius, they are preceded by an M. In this example, the temperature is 10 degrees Celsius and the dew point is -8 degrees Celsius. Altimeter settings are preceded by an A and reported in a 4-digit format in inches of mercury. Here, Denver's altimeter is reported as 29.901 inches of mercury. The last section of a METAR contains remarks and is identified by the contraction RMK. This section includes operationally significant weather, as well as the beginning and ending times of the specified weather phenomena. In this example, rain began at 35 minutes past the hour. At 55 minutes past the hour, the rain ended. Pilot weather reports, or PIREPs, also provide valuable information about current weather conditions and should be reviewed in a thorough weather briefing. No other observations are more timely than the ones made by a pilot. In fact, PIREPs provide the only means of directly observing cloud tops, icing, and turbulence. A PIREP is usually received and transmitted in a prescribed format. The letters UA identify the report as a routine PIREP, and UUA identifies an urgent PIREP. 2-letter codes differentiate each block within the report. For example, OV describes the location of the aircraft. TM tells you the time when the report was made. FL identifies the flight level. And TP tells you the type of aircraft flown. These first 5 blocks must be included in all PIREPs. The PIREP must contain at least one of several weather elements, also identified by 2-letter codes. These include SK for sky cover, WX for flight visibility and weather, TA for temperature, WV for wind, TB for turbulence, IC for icing, and RM for any remarks that might be included within a report. In printed form, PIREPs appear in this format. This sample PIREP from near Centennial Airport was issued as urgent. The aircraft was on the Denver 161 radial at 14 miles. The time of the report was 1939 Zulu, and the pilot was flying at 11,500 feet in a Mooney Mark 20. The pilot reported moderate to severe turbulence between 11,500 and 14,000 feet while en route from Farmington, New Mexico to Centennial Airport. Radar reports are another important source of weather information since they identify areas of precipitation at the time of the report. Each report can be divided into as many as 10 blocks of information. The first segment contains the location identifier and the time of the radar observation. This report is from Evansville and was taken at 1926 Zulu. The observation shows an area of echoes with 3/10 coverage consisting of light rain showers, which are decreasing in intensity. The next segment defines the boundaries of the area of precipitation using the azimuth and range from the reporting site. In this example, the points defining the area of echoes are 338 degrees at 90 nautical miles from Evansville, 111 degrees at 110 nautical miles, and 262 degrees at 125 nautical miles. The report continues by indicating that the area of precipitation is moving from 260 degrees at 30 knots. Finally, it shows that the maximum tops of the clouds are at 12,000 feet, located at 324 degrees at 39 miles. The predicted surface weather within a 5 statute mile radius from the center of an airport's runway complex is called a Terminal Aerodrome Forecast, or TAF. Each forecast is issued 4 times a day and is valid for a 24-hour period. The codes used in a TAF are similar to those used in a METAR. In this example of a terminal aerodrome forecast, you can find forecast wind, visibility if 6 statute miles or less, weather, and sky conditions. Let's take a look at a typical TAF. This forecast is for KDEN, Denver, Colorado. Following the 4-letter station identifier is the date and time of issuance. The first 2 digits are the date, immediately followed by the time in Zulu. This forecast was issued on the 9th of the month at 1745 Zulu. The next group indicates the valid period. In this case, the forecast is valid on the 9th of the month from 1800 Zulu through 1800 Zulu on the following day. The forecast is calling for winds from 220 degrees true at 20 knots. Visibility is expected to be 2½ miles with light rain showers. The ceiling is forecast to be 2,000 feet broken. When the wind direction fluctuates, or the wind speed is 3 knots or less, it is encoded as VRB. Cumulonimbus, CB, is the only cloud type included in a terminal aerodrome forecast. When the weather is expected to change during the forecast period, the TAF will indicate the change at the end of the report. For example, at Denver, from 0100 Zulu, the sky conditions are forecast to be clear through the remainder of the forecast. When a possibility exists for a change in the wind, visibility, weather, or sky conditions, and those forecast changes are expected to last less than an hour, they are preceded by the term TEMPO, or tempo. This report predicts that between 0400 Zulu and 0800 Zulu, visibility will drop to 3 statute miles associated with thunderstorms and rain showers. An overcast layer of cumulonimbus clouds with bases at 3,000 feet is also expected. BECMG, or becoming, is used when a gradual change in conditions is expected and should not last more than 2 hours. The forecast time of the weather is listed by a 4-digit number representing the beginning and ending hours of the change and follows the becoming indicator. When there is a 30 to 49% chance for the occurrence of thunderstorms or precipitation, you will see a probability group. Thunderstorms or precipitation expected to be present more than 50% of the time will be included in the prevailing weather or a tempo. Here, there is a 40% chance of 3 statute miles visibility along with thunderstorm and rain showers between 0000 and 0400 Zulu. This report also predicts that a broken layer of cumulonimbus clouds with bases at 3,000 feet is expected during this 4-hour time period. Now let's look at the area forecast, or FA, which also provides valuable weather information. Each forecast predicts the general weather conditions over an area the size of several states. You can use it to help determine en route weather as well as probable weather conditions at airports without terminal aerodrome forecasts. An area forecast is divided into 4 basic sections: communications and product header, precautionary statement, synopsis, and VFR clouds and weather. The Communications and Products header identifies the office issuing the forecast, the date and time of issuance, the valid times for forecast weather, and the states covered by the forecast. The precautionary statements, a standard note on each area forecast, indicate that thunderstorms imply possible severe or greater turbulence, severe icing, low-level wind shear, and IFR conditions. The statement in this example, see AirMet Sierra for IFR conditions and mountain obscurations, alerts pilots that IFR conditions and/or mountain obscurations may be occurring or forecasted to occur in a portion of the forecast area. Always check the latest AirMet for your area of flight. In addition, all heights not given in terms of mean sea level are noted in the forecast by the abbreviations AGL for above ground level or CIG for ceiling. This section of the area forecast is the synopsis, which contains a brief summary of the location and movement of fronts, pressure systems, and circulation patterns for an 18-hour period. This synopsis states that there is an upper-level trough in north-central Montana through southern Idaho that will move east into the plains by 00 Zulu with an upper-level ridge building over Washington, Oregon, and northern California. There is also a surface high pressure over eastern Washington and northern Idaho that will build southeastward into southwest Wyoming behind the cold front. The VFR clouds and weather portion of this section is broken down by states or areas and describes the cloud conditions, weather, and/or visibility that are marginal VFR or better. In this example, Arizona is forecast to have scattered to occasionally broken clouds in the northern half of the state. The southern and far eastern portions of the state are expected to have scattered clouds with bases at 15,000 feet AGL and a chance of isolated light rain showers after 1500 Zulu. Included in the VFR clouds and weather portion is a 12-hour forecast and 6-hour categorical outlook for each state. The outlook for this area is VFR. When weather conditions warrant, the National Weather Service will issue in-flight advisories in the form of AirMets, SIGMETs, and convective SIGMETs. Although classified as in-flight advisories, these reports are also included in computer printouts. These advisories notify pilots of the possibility of hazardous flying conditions, which may not have been forecast at the time of the initial briefing. An AirMet describes areas of turbulence, icing, sustained surface winds greater than 30 knots, ceilings below 1,000 feet and/or surface visibility below 3 statute miles, and mountain obscuration of sufficient intensity or extent. There are 3 AirMet designators. Sierra always represents areas of IFR, Tango always represents areas of turbulence, and Zulu always represents areas of icing. Here, AirMet Sierra is valid for Wyoming and Colorado and indicates areas of mountain obscuration and IFR conditions. SIGMETs describe non-convective weather conditions of greater intensity than those in AirMets. SIGMETs are issued for severe or extreme turbulence or clear air turbulence, severe icing, dust or sandstorms that lower surface or in-flight visibilities to below 3 miles, or volcanic ash. Anytime weather conditions meet or exceed these criteria, or are expected to occur within 2 hours, a SIGMET will be issued. Convective SIGMETs report areas of severe thunderstorms, tornadoes, heavy precipitation, hail of 3/4 inch or greater, wind gusts to 50 knots or more, embedded thunderstorms, and lines of thunderstorms. However, since conditions of severe or greater turbulence, severe icing, and convective low-level wind shear are normally associated with thunderstorms, these conditions are assumed to exist and are not specified in the report. Convective SIGMET bulletins are issued at 55 minutes past the hour and are valid for 2 hours. Appended to each convective SIGMET is an outlook valid for 2 to 6 hours after the issuance time. This outlook discusses further convective development with emphasis on lines or clusters of thunderstorms and severe or embedded thunderstorms. Another element of your weather briefing is the winds and temperatures aloft forecast. This forecast helps you calculate en route speed and performance figures for your aircraft. Winds and temperatures aloft forecasts are derived from information gathered by weather balloons released at 12-hour intervals. The forecast gives the wind direction in degrees from true north, wind speed in knots, and the temperature in degrees Celsius for selected altitudes. Forecasts for specific locations are indicated by station identifiers. Each identifier is followed by code groups which show the wind direction, wind speed, and temperature at specified forecast levels. The first two digits represent wind direction in tens of degrees, with the next two digits representing the wind speed. Where appropriate, the remaining digits record the forecast temperature. In this example, the coded group forecasts a wind from 200 degrees at 6 knots. The temperature at this altitude is forecast to be 13 degrees Celsius. Due to terrain influence, wind forecast information is omitted from any level that is within 1,500 feet of the ground. Likewise, the temperature is omitted from the 3,000-foot level and any other level which is within 2,500 feet of the surface. Since temperatures are always negative above 24,000 feet, the minus sign is omitted above this level. Notices to airmen, or NOTAMs, are usually included with printed weather reports. NOTAMs alert you to recent changes in the airspace system that could affect the safety of your flight. Here, a temporary flight restriction is in effect until further notice. This restriction is due to dynamite blasting, and only authorized flights may be conducted within 500 feet over the blasting area. In this program, you have seen a brief overview of some of the major printed reports and forecasts that are available to you in preparing for any flight you take. When interpreted correctly, these reports and forecasts help you understand the weather you will encounter in flight.
In addition to the printed reports and forecasts disseminated by the National Weather Service, there are also various graphic weather products available for your use. Some of the more common graphic products are the surface analysis, weather depiction, radar summary, and low-level significant weather prognostic charts. These charts are designed to give you the general weather picture over a large geographic region in a glance. The surface analysis chart is a good source for this type of information. Here, surface pressure, frontal areas, and surface weather information have been combined into a single graphic display. Low and high pressure centers are readily identifiable by large L's and H's. Isobars, connecting points of equal pressure, are plotted around these centers. They are normally drawn at 4 millibar intervals and are labeled with the last two digits of the barometric pressure. Here, the isobar labeled 96 represents 996 millibars. Frontal boundaries are noted by solid lines. The direction and type of front can be determined by the symbols attached to the line. The front shown here has pointed barbs on one side, which identify it as a cold front. Since the barbs are on the east side of the line, the front is moving in an easterly direction. Weather briefers may color cold fronts blue to help you identify them. Half circles identify this as a warm front. Again, the direction of movement is shown by the placement of the symbols on the frontal line. In this case, it is moving to the north. For ease of identification, warm fronts may be colored red. A combination of half circles and barbs on opposite sides of the lines is used for a stationary front. The line is usually colored with alternating red and blue segments. A line depicting an occluded front has both symbols on the same side and is usually colored purple. In addition to pressure and frontal information, the surface analysis chart provides weather observations for a large number of reporting stations located throughout the country. For each location, a station model provides the reported weather conditions at the time the chart was produced. Let's take a closer look at each element of the model. The identifier is printed below and to the left of the symbol. LAF represents Lafayette, Indiana. The circle itself is shaded according to the amount of cloud cover that is present. Here, 3/4 of the circle is filled, indicating a broken cloud layer. A wind pointer indicates the true direction from which the wind is blowing. You can read the speed using the barbs at the end of the wind pointer. Each long barb represents 10 knots, while each short barb is 5 knots. In this example, the wind is out of the southeast at 15 knots. A pennant represents 50 knots of wind, while a circle around the station indicates a calm wind. When clouds are present, the level and type will be depicted in the station model. Low clouds are shown below the station model, with middle and high clouds printed above the symbol. You can find the decoding information for these symbols in various FAA publications and at flight service stations. To the left of the station circle is the temperature and dew point. If there is precipitation or weather obscuring the visibility, the appropriate symbol will be printed between the temperature and dew point figures. The symbol here represents intermittent snow. To the lower right of the station, the precipitation over the last 6 hours is recorded in hundredths of inches. The atmospheric pressure measured in tenths of millibars is shown in the top right corner. You must add the decimal and prefix the number with a 9 or 10, whichever brings the value closer to 1,000. The pressure at Lafayette is 1,018.7 millibars. Below this reading is the amount and tendency of any pressure change over the past 3 hours. At this station, the pressure has decreased 0.7 millibars. To ensure that you have the latest information, you should note the time of the observation. It is shown in a date-time box in the lower left portion of the chart. Then, by comparing the current surface analysis chart with earlier ones, you can get an indication of how the weather systems are progressing. Another graphic display of the weather is the weather depiction chart, which can be very useful in determining general weather conditions and the locations of low clouds and visibility. This chart, like the surface analysis chart, uses a station model to present the reported weather at various locations. However, this model has been simplified, making it easier to read. Cloud coverage is shown in the same manner, but the pressure information, wind, temperature, cloud types, and station identifier are not plotted. Below the station circle is the height of the ceiling or lowest cloud layer in hundreds of feet. This station model is showing overcast skies at 10,000 feet AGL. If the visibility is 5 statute miles or less, it is printed to the left. Weather or obstructions to visibility may also be shown. The visibility at this station is 3 miles in fog. Although pressure and wind information is not provided on these charts, areas of significant weather are outlined to help with route planning. Shaded areas indicate IFR conditions and contain ceilings less than 1,000 feet and/or visibilities less than 3 miles. Areas of marginal VFR weather with ceilings between 1 and 3,000 feet and/or visibilities between 3 and 5 miles are shown in solid lines with no shading. Finally, weather depiction charts also give the position of fronts. This frontal information, when added to the areas of IFR and marginal VFR weather, will give you a very good picture of the general weather affecting your route. The radar summary chart is another graphic display that is frequently used by pilots and briefers. It is used to identify large areas of precipitation and hazardous weather that could affect your flight. Radar summary charts are developed by using reflected radar energy or echoes of the precipitation areas. The more severe the precipitation, the stronger the echo. Each radar observation station is then combined into one hourly map. The strength of the echo returns is shown by solid lines surrounding shaded areas. The outermost line indicates precipitation that is light to moderate. A second line within the echo depicts heavy to very heavy precipitation, while a third line shows where intense to extreme precipitation exists. A solid single line shows a line of echoes with the boxed SLD indicating that the echo coverage is 0.8 or greater along the line. The direction of movement of an individual cell is indicated by an arrow. The speed, 45 knots, is shown at the point of the arrow. The letters NE indicate areas with no echoes, while the letters TRW stand for thunderstorms and rain showers. Echo tops are encoded in 2 or 3 digits. You will need to add 2 zeros to determine the actual altitude. For example, the top of this cell is at 34,000 feet, and the top of this one is 19,000 feet. Because it is assumed that all precipitation displayed on the chart reaches the surface, the chart does not include a symbol to show the base of the echoes. An area which is under a severe weather watch will be marked with a dashed box and an alphanumeric identifier. In this case, WS0006 identifies this as a severe thunderstorm watch area. When an area is marked with a WT, it is identified as a tornado watch area. When using a radar summary chart, remember that radar only detects areas of liquid or solid precipitation. It will not, for instance, show areas of fog, and the actual cloud tops may be higher or lower than the figures shown on the chart. The charts we have seen so far in this program have all depicted observed weather conditions. Other charts, including the Low-Level Significant Weather Prognostic, or PROG chart, offer a forecast of future weather. PROG charts are divided into 4 panels. The top 2 contain 12 and 24-hour forecasts of IFR and marginal VFR conditions, turbulence, and freezing levels. These 2 panels forecast the weather from the surface through approximately 24,000 feet. The bottom 2 panels forecast the location of pressure and frontal systems, as well as the areas and types of precipitation on the surface itself. Areas of IFR conditions, where ceilings are expected to be less than 1,000 feet and/or visibilities less than 3 miles, are enclosed by solid lines. Scalloped lines enclose marginal VFR areas where ceilings are expected to be 1,000 to 3,000 feet and/or visibilities are forecast to be between 3 and 5 statute miles. Areas which are forecast to have moderate or greater turbulence are enclosed by dash lines and contain symbols indicating the intensity and altitude of the turbulence. In this case, moderate turbulence can be expected from the surface to 3,000 feet over this area of the United States. The position of the freezing level at specified altitudes is also shown on the chart. A zigzag line is used to identify the freezing level at the surface. Freezing levels above mean sea level are indicated by dashed lines drawn at 4,000-foot intervals. On the lower panels, fronts and pressure centers are presented in the same manner as they are on surface analysis charts. In this example, this high has a barometric pressure of 1,022 millibars. Solid lines are used to denote areas of precipitation. Symbols are inserted to denote the type of activity expected. For example, 2 dots indicate rain, while 2 star symbols represent snow. A mixture of precipitation is indicated by showing 2 pertinent symbols separated by a slash. These symbols represent rain showers and thunderstorms. A bold dash line is used to separate precipitation with contrasting characteristics within an outlined area. For example, This dashed line separates an area of snow from an area of rain. Continuous precipitation is a dominant and widespread event, and therefore is shaded. Intermittent precipitation is a periodic and patchy event and remains unshaded. Shading is also used to denote the amount of precipitation projected in a specified region. Areas with more than half coverage are shaded, and half or less coverage unshaded. The charts that have been presented in this program are but a few of the graphic weather products that are available for your use. As we have seen, charts of these types are very useful for obtaining a brief, general overlook of the existing and forecast weather along your intended route of flight and the surrounding areas. In previous segments, you learned how to interpret printed reports and forecasts as well as graphic weather products. But as a pilot, how does this information get into your hands? You can retrieve weather information from a wide variety of sources. Government facilities and private companies make weather reports and forecasts available by phone, television, fax, radio, and the internet. First, let's take a look at the sources of pre-flight weather information available to you. The most common source of pre-flight weather information is the Flight Service Station, or FSS. Flight service stations are FAA-operated facilities spanning the contiguous United States as well as Alaska and Hawaii. You may encounter the term Automated Flight Service Station, or AFSS. This term is sometimes used to differentiate the current FSSs that employ advanced technology from the former non-automated FSSs. An FSS typically offers a number of services, including pre-flight weather briefings, IFR and VFR flight plan processing, assistance for aircraft that are lost or in distress, and aid for search and rescue operations. Some flight service stations also have the ability to provide in-flight weather information in the form of En route Flight Advisory Service, or EFIS. If you happen to live in a city where an FSS is located, you can visit the station and receive pre-flight weather services in person if the briefers are able to handle your request at that time. Due to the limited number of stations in the U.S., however, a telephone briefing is a much more common means of receiving weather information. You can reach a flight service station on the ground by simply dialing a toll-free number anywhere in the U.S. When you dial 1-800-WXB-RIEF, you will be connected with the FSS nearest your location. The FSS phone system allows you to access a pre-flight weather briefer, along with other services such as FastFile, a flight plan filing tool. When you speak with a pre-flight briefer, you can request one of three types of weather briefings: an Outlook briefing, a standard briefing, and an abbreviated briefing. Before you can receive a briefing, however, you must provide some background information regarding your flight. This allows the briefer to tailor the weather information to your specific needs. An Outlook briefing is used when your departure is 6 or more hours away. This type of briefing is very useful for getting an overall picture of the general weather trends that may affect your flight. As your departure time nears, a standard briefing is necessary to obtain the most complete and in-depth weather data. A standard briefing is comprised of 12 separate and sometimes lengthy elements, so be prepared to write when you call. The briefer normally provides you with the following information: reported and forecast adverse weather conditions, information regarding whether or not VFR is recommended based on the current and forecast weather, an overall synopsis of weather systems, the current weather conditions, the en route weather forecast for your route of flight, the forecast for your destination airport, the winds and temperatures aloft forecast, NOTAMs, any air traffic control delays if applicable, a request for pilot reports, the availability of EFIS or FlightWatch, weather updates, and any other information you request, such as military activity along your flight route. Just prior to your departure, you may elect to check the weather one more time. An abbreviated briefing allows you to request one or two specific items and be advised of any changes in the weather since your last briefing. To expedite this briefing, be sure to include as much background information as possible, including the time and source of your last briefing. If you do not need to speak with a weather briefer, but you would like current weather information to aid in your pre-flight planning, some FSSs offer the Telephone Information Briefing Service System, or TIBS. You can access the TIBS recordings using the FSS 1-800 number. Typically, these recordings include route and/or area briefings for specific locations in the FSS region.
This recording prepared at 1408 Zulu. Briefing summary of current weather in eastern Colorado. Valid until 1500 Zulu. Summarize current conditions. A few clouds at 9,000 to 11,000 and high scattered cirrus. Visibility is unrestricted. Winds are generally northwesterly to northeasterly.
The TIBS system is recommended for preliminary briefings only and should not replace a standard weather briefing. If you have any questions about the recorded information, you can remain on the line to access a weather briefer. Be sure to provide the briefer with any background information in order to expedite the process. Another system you can use to receive complete weather briefings is the Direct User Access Terminal Service, or DUATS. DUATS is a free service that can be accessed on the Internet or with a modem and a 1-800 number. You can obtain all the items of a standard weather briefing through DUATS, as well as selected reports for specific locations. You can also file both VFR and IFR flight plans. DUATS, however, does not provide any details on military activities. You'll need to contact a flight service station for this information. You are required to have a current medical certificate to access the DUATS system. Further information regarding the DUATS service can be found in the Aeronautical Information Manual. In addition to DUATS, a number of organizations offer weather information by phone or on the Internet. While many of these sites and services are free, some require membership or specific user fees. Just one of many Internet sites providing weather information is the National Weather Service website, which is operated by NOAA, a weather service branch of the U.S. government. While websites are excellent sources of pre-flight weather data, the information presented may not be the most up-to-date and should not be used in place of a complete weather briefing from an FSS or the DUATS system. Jeppesen also provides several weather resources for pilots, such as JepFax, a worldwide weather fax service available for a small user fee. A complete listing of Jeppesen weather products, including JepFax, can be found at jeppesen.com or at flightneeds.com. Now that you've discovered where to obtain weather information prior to flight, let's explore how you can get updated weather information while airborne. One of the best sources of en route weather is En route Flight Advisory Service, or EFIS, also known as FlightWatch. This service is available from selected flight service stations. The frequency for FlightWatch is 122.0. After giving the EFIS specialist the details concerning your flight and your request, the briefer relays the latest weather information. You can also access weather data by monitoring selected VOR and NDB stations. These facilities normally provide local weather information updates or weather advisories. One such source of en route advisories is the Hazardous In-Flight Weather Advisory Service, or HIWAS, which is continuously broadcast over selected VORs. Information available through this system includes airmets, SIGMETs, convective SIGMETs, summarized severe weather forecast alerts, center weather advisories, and urgent PIREPs. The nav aids and frequencies used for HIWAS can be found in the Airport Facility Directory. Nav aids with HIWAS capabilities are also noted on aeronautical charts.
HIWAS for Miami Center area, recorded at 1845 Greenwich. Convective Sigmet 17 Echo. Between Key West and 50 nautical miles west of Vero Beach. Line of thunderstorms 25 nautical miles wide.
Other in-flight services which provide surface weather observations include the Automated Weather Observing System, or AWOS, and the Automated Surface Observing System, or ASOS. These systems record surface weather observations and automatically transmit real-time weather.
Denver Centennial Airport. Automated weather observation 2116 Zulu. Wind 040 at 12.
AWOS and ASOS broadcasts can be received up to 25 nautical miles from the station and up to a maximum altitude of 10,000 feet AGL. These stations are also accessible on the ground by phone. AWOS and ASOS facilities, frequencies, and phone numbers are listed in the Airport Facility Directory and the J-AID, as well as noted on aeronautical charts. As you have seen, there are numerous weather sources available for your use, and more methods to obtain accurate weather data continue to be developed. Additional information can be found in the FAR-AIM, advisory circulars, and other sources. You should always receive a pre-flight briefing before your departure. While en route, take advantage of EFIS and other en route information services to keep abreast of changes in the forecast weather. Fly safe by staying advised of current and expected weather conditions. With a wide selection of services available, obtaining the required weather data for your flight is both quick and easy.
Modern aircraft systems have become so reliable that emergencies seldom occur. If a problem does arise, you need to be able to handle it quickly and efficiently, particularly if you're in IFR conditions. As the pilot, you are the person responsible for the safety of the flight. The Federal Aviation Administration recognizes this fact and allows deviations from the FARs to the extent necessary to ensure this goal. With this emergency authority, however, comes responsibility. You're expected to exercise reasonable judgment in all flight decisions. In an emergency situation, if you deviate from any ATC clearance, you must notify ATC of that deviation as soon as possible. In addition, if you're given priority by ATC, you may be asked by the ATC facility concerned to submit a written report of the circumstances surrounding the emergency deviation. Your ability to recognize conditions which can produce an emergency situation will increase with your flying experience. Whenever you feel that a potentially dangerous or unsafe condition exists, you must take the appropriate action and advise ATC. Although the steps you take will vary with the situation, the AIM establishes some guidelines. For example, if an emergency occurs when you're operating under instrument flight rules, you should immediately inform ATC of your problem and continue squawking your assigned transponder code unless directed to change to another code. If you are unable to immediately communicate with an ATC facility, you should squawk 7700, the emergency code. If you can't establish contact, use the emergency frequency of 121.5 megahertz. Most flight service stations, radar facilities, and control towers continuously monitor this frequency for distress transmissions. If you're still unsuccessful, try contacting the nearest flight service station or ATC control tower. If you're in a distress situation, such as a fire or structural damage, start your transmission with the signal Mayday, Mayday, Mayday. If the situation is not as critical, such as not being sure of your position or whether you can make your destination on the amount of fuel you have, you're in an urgent situation. With this type of emergency, you should precede the transmission with pan, pan, repeated 3 times. You should also give the controlling agency as much of the following information as necessary: the nature of the emergency, the weather conditions, such as if you're in VFR or IFR conditions, your intentions, and the extent of any needed assistance. They also need to know your heading, altitude, and how much fuel you have on board. In this way, they can assess the situation and give you radar vectors to VFR conditions or to the nearest airport. If the situation warrants, ATC will also give you priority and clear the airspace of other traffic.
Chicago Center, Cessna 52241. Chicago Center, Cessna 52241.
Emergency situations can be created or compounded by the loss of two-way radio communications. Radio failure can be attributed to many causes. A stuck or malfunctioning microphone or headset, broken speaker wires, or incorrectly set avionics switches can all produce partial or complete communication loss. If a problem does occur, you should check to make sure that your radios are set properly and that they are getting electrical power. If you have a spare microphone or headset, you might want to use it because the problem could just be in the microphone or speaker. If you can't restore two-way communications, you should alert ATC by squawking code 7600. Since a communications failure can seriously disrupt the flow of IFR traffic, the FARs and AIM outline specific procedures to be followed in IFR conditions. It is important to know and follow these procedures since the routing of other air traffic is based on your compliance. For example, if you experience communications failure while in VFR conditions, or if you encounter VFR conditions during the failure, you should remain VFR if possible and land as soon as practical. However, the term "as soon as practical" does not mean that you have to land at an unsuitable airport or at a closer airport if you're just minutes short of your destination. If IFR conditions prevail at the time of the communications failure, exercise your options in the following sequence. You should continue the flight by the last route assigned by ATC. If you are receiving radar vectors, proceed direct from the point of radio failure to the fix, route, or airway specified in the vector clearance. When no route has been assigned, continue the flight by the route ATC has advised you to expect in a further clearance. If none of these alternatives apply, proceed according to the route filed in your flight plan. In addition, fly at the highest of the following altitudes: the last assigned altitude, the minimum en route altitude for each route segment, or the altitude that ATC has advised you to expect in a further clearance. Let's see how this works. Your flight has been cleared eastbound along Victor 70 from Monroeville to Eufaula. You've been cleared to maintain 2,000 feet and to expect 3,000 feet at Chaff intersection. If you experience communications failure in IFR conditions, you should maintain the assigned altitude of 2,000 feet to Chaff intersection. Then climb to the expected clearance altitude of 3,000 feet. At Routel intersection, begin a climb to 4,500 feet, the minimum en route altitude for this segment. After Krenz, the MEA lowers to 2,400 feet, but you shouldn't descend lower than your expected clearance altitude of 3,000 feet. Maintain this altitude to the Eufaula VOR. Once you arrive at your destination, ATC will provide adequate traffic separation for each published instrument approach procedure serving the destination airport. You may use whichever approach you deem appropriate. However, you should not begin your approach before your estimated time of arrival. You can determine your ETA by adding the filed or amended time en route to your departure time. The lost communications procedure just presented covers a few of the specific corrective actions required for some in-flight communications failures. You must recognize, of course, that emergency situations may be caused by other aircraft system failures or by encounters with various weather hazards. Whatever the emergency, you should always assess the problem and act accordingly in the interest of safety. Good pre-flight planning, pre-flight inspection, and attention to aircraft systems helps you prevent potential emergency situations and greatly adds to the overall safety of your flight.
Your instrument rating allows you to fly into thousands of airports, even if the weather is below VFR minimums. This rating shows that you're able to control the airplane solely by reference to instruments. However, actual IFR flight is very different from the controlled training environment of flying under the hood with your instructor by your side. Since the demands of instrument flight impose heavy pilot workloads, especially in high-density terminal areas, you need to gather all available information when planning for and making an instrument flight. As with any flight, your first priority is to thoroughly evaluate yourself. There are several key questions you should ask. For example, do you meet the recent IFR experience requirements of FAR 61.57? How do you feel about your ability to fly the types of approaches available at your destination and alternate? For instance, has it been a while since you've flown an NDB approach? How is your emotional and physical health? If you're distracted by a stressful problem, you might not be able to handle the demands of IFR flight. Don't try to kid yourself into thinking that there's nothing wrong. Next, evaluate your airplane. Just because you're instrument rated and current doesn't mean your airplane is capable of making the trip. For example, if the approach at your destination requires DME, does your airplane have DME equipment? And is it operational? Does it have dual VORs to decrease your workload? And have they been checked within the last 30 days? What about the other aircraft systems? Have they had the proper inspections? How does your airplane's performance capability compare with the altitude demands of your proposed route? Many areas have MEAs that can exceed your airplane's altitude capabilities. Also, consider the aircraft's ability to deal with structural icing. Is it certified for flight into known icing conditions? Once you've determined that you and your airplane are ready for flight, turn your attention to the environment. This includes the current and forecast weather along your entire route, as well as potential alternates. Include the ATC system as part of this analysis. Will you be flying in a radar or non-radar environment? What is the most likely sequence of facilities you will contact? All of these elements come together to form the situation. There is a direct relationship between your awareness of the situation and safety. With that in mind, let's look more closely at some of the factors which may influence your decision to make the flight. Obviously, one of your biggest concerns is the weather. Many times it affects your final route selection or your decision whether or not to make the trip. The key to obtaining a good weather briefing goes far beyond gathering basic weather data. You must be able to interpret and understand the information. If you're not sure of what the specialist is telling you, or what the reports, forecasts, and charts indicate, then ask for clarification. Remember that, although the specialist provides you with an abundance of weather information, the final decision to make the flight is entirely up to you. A primary concern is the predicted weather for the destination airport at your time of arrival. You have several factors to consider here. How does the expected weather compare to the published landing minimums? How does it compare with your level of proficiency? The answer to this question may be affected by your level of IFR experience, your familiarity with the airplane, and your IFR currency. Based on this analysis of your proficiency level, you might want to set your personal landing minimums higher than those published. Now let's look at some of the pre-flight considerations. In addition to the nav log, consider highlighting the en route chart, including all nav aids and fixes. In this way, you can quickly orient yourself on the chart. As to what information you should include on your nav logs, or what information you should highlight on the charts, just remember that as long as you can find what you're looking for, too much information is better than not enough. Planning the approach at your destination is also an important consideration. Study each chart carefully and mentally fly the approach. This includes the arrival routes needed to transition from the en route phase to the approach, the frequencies, and the initial approach fixes. Look at the headings, altitudes, distance information, and the missed approach procedure to see if there is anything out of the ordinary and to get an idea of what to expect. Then move to landing minimums and check the DH and MDA. Also look for any information that indicates additional equipment or special procedures, as well as timing information if appropriate. In addition, review the runway layout and runway and approach light systems. When you examine your charts, be sure to include any possible alternates. Don't wait until you're en route to your alternate before you look at those approaches for the first time. Situational awareness does not stop with just flight planning. It also includes such things as cockpit management. After you've completed your pre-flight inspection, take a few minutes to organize the flight material before starting the engine. This helps you locate information quickly once you're en route. Along with arranging everything in a logical order, have every item close by which you might possibly use during the flight.
Warrior 81312, cleared to the Hutchinson Municipal Airport as filed. Maintain 7000, maintain runway heading for radar vectors. Departure control 120.9er, squawk 4127.
When you obtain an IFR clearance, take a moment to study it and to envision what the clearance is authorizing you to do, especially if any part has changed from your filed route. If you have any doubt about the clearance, read it back or ask for a clarification. During your pre-takeoff check, be especially aware of the flight instruments. Are the gyros up to speed? Is there sufficient vacuum? Is the attitude indicator aligned with the horizon? Then, before departure, you might want to set one navigation receiver to the approach facility in use at the departure airport and the other to your first en route facility. In this case, if you have to return quickly to the airport for any reason, you'll be set for the approach. An important element of the decision-making process is recognizing that a change has occurred and then determining the proper course of action. For this reason, keep track of your position and frequently include the aircraft's engine, electrical, and other systems instruments in your normal scan. For instance, by checking the vacuum indication, you'll notice if an abnormal reading occurs. This can help with the early identification of malfunctioning attitude and heading indicators. Since part of IFR cockpit management includes finding ways to make your job easier, many instrument pilots use a headset to facilitate communications with ATC.
Warrior 312, turning left to 060.
Not only does the headset reduce the time required to initiate a communication, but it lets you talk to controllers without diverting your attention from the instruments.
Warrior 312, contact Kansas City Center on 125.2.
Warrior 312, Kansas City Center on 125.2.
You might also choose to use a lap or knee board to copy ATC clearances, updated weather, and to help keep your flight material organized. If you have one, an autopilot can significantly reduce your workload. With the system engaged, you can relax somewhat from the demands of flying the airplane. This allows you more time to review your route or the approach chart. However, when using an autopilot, make sure you monitor its performance. It is possible for an autopilot to fail or become unreliable. Probably the most challenging and stressful element of a single-pilot instrument flight is the approach and landing. Flying into a terminal area can be fast-paced. Besides controlling the airplane, you must obtain ATIS, communicate, fly the procedure, identify nav aids, intercept radials, prepare the airplane for landing, identify the runway environment, and perform a landing. This is where your organizational skills come into play. By being able to anticipate what is coming next, you'll be able to reduce the stress during this phase of the flight. This is one of the reasons you visualize the flight before actually performing it. As you near the missed approach point in instrument conditions, you must make a decision to continue with the approach or perform a missed approach. During your training, you're taught to immediately execute a missed approach when you reach the missed approach point and cannot identify the runway environment. Sounds simple, doesn't it? However, during an approach in actual IFR conditions, the natural tendency is to want to land the airplane, especially if you can see the ground, but not necessarily the runway. What if you can see approach lights, but their alignment is off? What if you think you see the runway? Or you think the visibility is above minimums? This is when your IFR decision-making skills pay off. Since vague visual cues can cause confusion and disorientation, you must not continue an approach beyond this point unless you know you can meet all the requirements to continue visually to a landing. Many accidents have occurred because pilots have made the wrong decision by continuing the approach without being able to positively identify the runway or to maneuver the aircraft safely to it. It's not worth the risk. To increase the margin of safety, many commercial operations require a crew in the cockpit. When this is done, guidelines or standard operating procedures are established. The crews are taught these specific procedures and are trained to interact as a team in order to obtain the highest level of safety. Likewise, although regulations do not require it, you might want to have another person along during instrument conditions to help with the flight. Even if this person is not a pilot, there are numerous things the passenger can do to assist with the trip. One of these is helping you keep the cabin organized. If your passenger happens to be a pilot, your workload can be distributed significantly. For instance, you can have the other pilot handle the radios and identify nav aids, as well as help you monitor your current position and altitude. However, another pilot can either make your job easier or can cause confusion if your roles are not clearly defined. The delegation of authority and responsibility must be explicitly worked out prior to the flight, or there is an increased chance of a mistake occurring. In other words, you must know who is going to do what. For example, who will be responsible for communicating with ATC? Who will copy the clearances? And who will adjust the altimeter when you obtain a new setting? As you can see, there is great potential for confusion that could lead to a drastic error, no matter how much experience you both have. So take the time to determine each person's responsibilities and communicate with one another to avoid overlooking an essential procedure. Just remember, as pilot in command of the flight, you are the one responsible for the airplane's operation. As you've already learned, flying is a combination of events which requires you to make a continuous stream of decisions. During an IFR flight, you'll experience a whole new set of decisions affecting you, your airplane, and the environment. By practicing the decision-making skills and doing those things which will lessen your workload while flying, you will enhance the safety of your flight. Up to this point, you've learned most of the skills required to fly the aircraft solely by reference to the instruments. Soon, you will be ready for your first IFR cross-country flight. Although thorough pre-flight planning is essential for any cross-country, it becomes even more important when the flight is conducted under instrument rules. By regulation, you're required to acquaint yourself with all available information, including the weather, fuel requirements, and any known traffic delays. You must also have an alternate course of action in case your original flight cannot be completed as planned. To illustrate the proper steps, let's plan a flight between Miles City, Montana, and Jamestown, North Dakota. The night before your flight, you check the weather along your route and find that high pressure dominates the Miles City area. The forecast is for VFR conditions to prevail into central North Dakota. There is also a low-pressure system located in southern Minnesota with a stationary front extending northward into Canada. Both ahead of and behind this front, there have been widespread areas of low ceilings and poor visibility. However, the IFR weather is forecast to move out of the Jamestown area by the time you arrive. Current weather at Jamestown is 300 overcast with a half-mile visibility. Because the weather might not move as quickly as forecast, you decide to play it safe and plan for an IFR flight. You begin your planning by gathering up the materials you'll need, including the en route chart, approach charts for the departure, destination, and alternate airports, and the airport facility directories for the area you're flying through. You will also need a navigation log, flight computer, and any other material you would normally use to plan a cross-country flight. The first thing you should do is check to see if there is a preferred IFR route for your flight. Preferred IFR routes are listed in the en route section of the Jeppesen Airway Manual and in the Airport Facility Directory. To determine if preferred IFR routes exist, look for the city near your departure point. There are no preferred IFR routes between Miles City and Jamestown. You should also check for any special arrival and overflight routes. Again, there is nothing for your flight. By referring to the chart, you determine the easiest and most direct route is to follow Victor 2 through Dickinson and Bismarck, and then to Jamestown. While you're looking at the chart, you should also take the time to select a possible alternate in case a diversion is necessary. Bismarck seems to be a good choice for a couple of reasons. One, it has an instrument approach, and two, it is along your route of flight. Remember, the IFR conditions are moving to the east, so if the weather is good when you pass over Bismarck, it should remain the same or get better if it becomes necessary to backtrack. Once you have the route in mind, record the necessary information on the navigation log. This includes the fixes, route, and distances between fixes. You should also note the MEA for each segment. The highest is 6,000 feet between Miles City and Dickinson. Then consult the chart NOTAMs to see if any of the navigation aids along your route are affected. Although the Dickinson DME is temporarily shut down, this outage shouldn't affect your flight, since DME is not required to navigate on Victor 2. However, you won't be able to receive distance measurements from Dickinson, so you'll have to keep track of your position by using other VORs in the area. You'll want to keep this in mind when selecting your cruising altitude. Once the route is established, you need to check the approach charts for more specific information. First, you need to find out if there's an IFR departure procedure for your departure airport. Miles City doesn't have either one. It's also a good practice to study the approach charts at the departure airport in case you must make an unscheduled return after you take off. Using the approach chart, check to see what communications frequencies are used at the airport and record them on the nav log. Turning to your destination airport, check to see if there's a standard terminal arrival route. You find that there isn't a star for this area. However, Jamestown does have a variety of approaches, including an ILS with minimums of 200 feet and a half-mile visibility. You should also take a few minutes to study the Jamestown Airport diagram. Familiarity with the taxiways and runways can be very helpful for ground operations and for orientation if you need to make a circling approach. You should also review the airport information of your possible alternate. In addition to the approaches available, you should check the alternate minimums, so you'll know if you can use Bismarck when filing for an alternate. In this case, the minimums are 602 using the ILS approaches, or 802 when using the Radar 1 or VOR-A approaches. Referring to the Airport Facility Directory, check the listings for the destination and alternate airports for such things as fuel availability, services, and special airport precautions. For example, at Jamestown, the airport is attended continuously, and you should be alert for birds on and in the vicinity of the airport. Before your flight, you may also want to brush up on ATC procedures by reviewing the Aeronautical Information Manual. Although it is not necessary for every flight, it is a good practice to periodically review the AIM to keep abreast of any recent changes. The morning of the flight, you should call the flight service station for a standard weather briefing to determine if the weather has improved as forecast. The briefing reveals that the expected improvement in conditions did not occur. IFR weather still dominates eastern North Dakota and Minnesota. Miles City is currently reporting good VFR weather with 10,000 scattered and 30 miles visibility. Dickinson is reporting 6,000 broken and 15 miles visibility. Bismarck is currently IFR with a 2,000-foot overcast and 2 miles visibility. At Jamestown, your destination, the last reported weather was 700 overcast and 2 miles visibility, with surface winds from 310 at 6 knots. Winds aloft for the route are generally westerly at less than 10 knots through 12,000 feet for Montana and western North Dakota, and light and variable through 12,000 feet for eastern North Dakota. NOTAMs indicate that the Jamestown ILS runway 31 glide slope is out of service. After gathering all the weather information, you realize you'll have to file for an alternate, since the forecast weather at Jamestown is below 2003. You should then compare the current and forecast conditions with the available approaches and minimums. With the surface winds at Jamestown from 310 at 6 knots, you'll probably fly a straight-in approach and landing on runway 31. The reported weather is 500 feet above the lowest approach into Jamestown, but with the glide slope out of service, the landing minimums have increased to 1,880 feet, which is still 315 feet below the reported ceiling. After reviewing the winds and temperatures aloft forecast, you select a cruising altitude of 7,000 feet. This altitude keeps you above the minimum en route altitudes and conforms to the IFR cruising altitudes. It should also let you receive the necessary VORs during the section of the flight when you won't be able to receive DME information. Using the forecast winds at that altitude, compute the estimated ground speed and the estimated time en route between checkpoints. This also includes the information back to your alternate. The fuel requirements for this flight include enough to fly from Miles City to Jamestown, then to the alternate, plus a 45-minute reserve at cruise power. You determined that you need a minimum of 44 gallons. After filling out the flight plan, you're ready to go. Because IFR flight plans require at least 30 minutes for processing, you may want to file at this time so it will be available when you're ready to depart. Before you leave, however, you might want to visualize the flight. For example, after departure, you should expect to quickly intercept the 062 radial of Miles City Vortac, which is Victor 2. Also, you can expect to contact Salt Lake City Center on 126.85. While on the airway, you know that you won't be able to receive DME from Dickinson, so you'll need to determine your position by tuning in Williston on 116.3. When within 20 miles of Dickinson, you'll likely be told to contact Minneapolis Center on 135.2. Over Bismarck, you'll want to check the weather in case you have to divert back here if you can't get into Jamestown. With the winds at Jamestown, you figure you'll be cleared for the localizer approach to runway 31. If this happens, you'll most likely fly to the Jamestown Vortac. Then you'll navigate to the LOM and perform a procedure turn to get lined up for the approach. To do this, you'll fly outbound on the 126-degree radial of Jamestown for 5.8 miles, or track to the Sabin LOM. From there, you will be using the localizer frequency of 109.3 to track outbound for approximately 2 minutes. Your outbound course will be 127 degrees. You'll complete the procedure turn by turning left to a heading of 082 degrees. After 1 minute, you'll make a 180-degree right turn and fly a heading of 262 degrees to intercept the localizer inbound. Since the glide slope is inoperative, you'll begin your descent at the final approach fix, which is Sabin outer marker, or the 6.4 DME fix of the Jamestown localizer, not the VOR. The MDA for this approach with the glide slope out will be 1,880 feet. You will probably fly the approach at a ground speed of 70 knots. That means you'll be at the missed approach point 4 minutes 22 seconds after passing the final approach fix. You can also identify the missed approach point when you're at Jamestown localizer's 1.3 DME fix. If you don't have the runway environment in sight at that time, you'll perform a missed approach, which is to climb to 3,200 feet, then make a right turn and proceed direct to the Sabin LOM and hold. Then, depending on the weather conditions, you'll either request another approach or request a clearance to your alternate. You might also want to look at the other approaches at Jamestown to see if there's anything unusual which might cause you a problem. By visualizing the flight before you actually get in the airplane, you've formulated a plan of action, which should make the flight easier, safer, and less stressful. As you have seen, a good planning sequence is important for any IFR flight. Development of good IFR planning skills can eliminate disorganization and assist you in your in-flight decision-making. With a good route choice, an understanding of the weather, and a knowledge of the factors that could affect your flight, you will not only save time and money, but will greatly reduce the possibility of an unpleasant surprise during your trip.
As you progress in your flying, you will probably be exposed to more sophisticated aircraft, and along with these sophisticated aircraft come advanced systems. For example, high-performance aircraft may be equipped with fuel injection systems, turbochargers, constant speed propellers, advanced environmental control systems, de-icing or anti-icing systems, and retractable landing gear. In this presentation, we'll look at these systems in detail and provide you with a basic understanding of each one. Since the specific operating procedures for each system vary from one manufacturer to another, you should always consult the pilot's operating handbook or aircraft flight manual prior to operating any unfamiliar system. In an effort to gain the maximum amount of power from small lightweight aircraft engines, manufacturers have devoted a great deal of engineering research to advanced fuel induction systems. One of the most successful of these is fuel injection. Unlike a carburetor which mixes fuel and air prior to reaching the intake manifold, a fuel injection system injects fuel into the intake port, where it is mixed with air just prior to entering the cylinder. This allows for an even distribution of fuel to the cylinders and a more uniform mixing of the fuel and air. Let's quickly look at the components of a typical fuel injection system. The first component that we'll look at is the auxiliary or boost pump, which is usually an electric pump and serves several purposes. Its primary function is to pressurize the injection system prior to engine start. This forces fuel through the lines. The auxiliary pump also maintains fuel pressure in the event the engine-driven pump fails. The next component is the engine-driven fuel pump. Once the engine is started, this pump pressurizes the system by taking fuel from the tanks and sending it to the fuel injector unit. In some systems, the fuel pump supplies more fuel than the injector unit needs. In this case, the excess fuel is routed back to the tank through a return line. In other systems, the fuel is strictly metered and no return line is required. After the fuel is pressurized by the fuel pump, it moves into the fuel injector unit. Here, valves meter the fuel according to the mixture setting and the flow of air into the engine. The metered fuel is then sent to the fuel flow divider, or fuel manifold, which is located on the top of the engine. It's designed to divide the fuel evenly between each of the fuel injection nozzles. Within the divider, there is a set of valves that automatically shuts off the flow of fuel to the engine when the mixture is placed in the idle cutoff position. After the metered fuel leaves the flow divider, it's injected into the engine through the injector nozzles located on each cylinder head. At this point, the fuel is mixed with the air in the induction manifold just outside the intake valves and combustion chamber. A fuel flow indicator, calibrated in pounds or gallons per hour, is connected to the outlet of the flow divider. It measures the pressure being applied to the discharge nozzles. Now that you're familiar with the basic components of a fuel injection system, let's look at some of the advantages fuel injection has over carburation. As mentioned earlier, one advantage of fuel injection is the even distribution of fuel to each cylinder. Let's look at why this is beneficial. On a conventional carburetor system, the metering and vaporization takes place at the beginning of the induction system. Notice how the center cylinder is closer to the carburetor than the cylinders at each end. This results in an uneven distribution of the fuel-air mixture. The ideal solution for this would be to have a carburetor at each cylinder. This is what a fuel injection system does. The injection nozzle acts just like a little carburetor, delivering equal amounts of fuel to all cylinders. This allows for a smoother running engine with more horsepower for the same amount of fuel. In addition, the engine will operate at lower temperatures. This decreases the chance of experiencing detonation or pre-ignition and increases engine life and reliability. Another advantage of fuel injection is that it is not susceptible to carburetor icing. Float-type carburetors are highly susceptible to icing due to where vaporization occurs. As intake air passes through the venturi, it cools. Further cooling occurs during the vaporization process. This drop in temperature can cause moisture to freeze and adhere to the internal parts of the carburetor. In a fuel injection system, there is no significant temperature drop across the throttle valve, so icing is unlikely. In addition, the fuel is vaporized at the cylinder head, where increased temperatures make icing virtually impossible. One place where ice can accumulate in a fuel injection system is on the air intake. If this happens, all air could be cut off to the engine, causing it to quit. To prevent this from happening, some induction systems have an alternate air door. When opened, air from inside the cowling is taken into the induction system. Although this allows the engine to keep running, the reduced airflow and increased temperature affects the amount of power the engine can produce, much like the effect carburetor heat has on a carbureted engine. Although it may sound like fuel injection is the perfect system, it does have some drawbacks, the most significant being the increased possibility of vapor lock. Vapor lock occurs when vaporized fuel blocks the flow of liquid fuel to the fuel injection system. The reason fuel injection systems are more likely to experience vapor lock is because there are more fuel lines in close proximity to the engine and the heat it produces. If temperatures are hot enough, the fuel inside the lines vaporizes, resulting in low fuel pressure or engine failure due to fuel starvation. Fuel-injected airplanes that are flown frequently with only short stops between flights are highly susceptible to vapor lock. This is because some of the heat given off by the engine is absorbed by the fuel lines, causing the fuel to vaporize. Vapor lock can usually be remedied by turning on the auxiliary fuel pump and forcing cooler fuel through the system. The last topic we'll discuss is starting procedures. Although the starting procedures vary between manufacturers of fuel-injected engines, all of them have one thing in common. That is, if the engine is cool to the touch or is being started for the first flight of the day, the system will have to be primed. This is accomplished with the auxiliary fuel pump. With the throttle and mixture set according to the POH, turn on the electric fuel pump and monitor the fuel flow indicator. When a sufficient fuel flow rate is noted, continue with the specified starting procedures. A common area of difficulty with fuel injection is starting a hot engine. As mentioned earlier, hot engines cause fuel in the fuel lines to vaporize. Again, the auxiliary fuel pump is used to purge the system of the vapor lock. When doing this, you want to make sure you follow the manufacturer's procedures to reduce the chance of flooding the engine and possibly starting a fire.
Another aircraft system that helps increase performance is turbocharging. Let's take a look at how turbocharging works and discuss some of the unique characteristics of operating an aircraft that is equipped with a turbocharging system. As you know, when you climb, the ambient air pressure decreases approximately 1 inch of mercury for every 1,000 feet. What this means is that there is less air available for combustion at higher altitudes. Because of this, normally aspirated engines are not able to produce maximum manifold pressure with an increase in altitude. In order for a reciprocating engine to overcome this problem, turbochargers were installed as a means of getting more air into the engine. With a turbocharger, intake air is compressed before it enters the combustion chamber. This allows the engine to obtain higher manifold pressures, which equate to increased engine output. To better understand how a turbocharger works, let's take a brief look at the components of a typical system. There are 3 components that are common to all turbocharging systems. They are the compressor, the turbine, and the wastegate. As air enters the intake, it passes through a compressor where it is compressed by the centrifugal force created by the impeller blades. The compressed air is then routed from the ring surrounding the impeller through the throttle body to the cylinder. The compressor is driven by a turbine which is propelled by the engine's exhaust. If all of the exhaust from the engine were allowed to pass through the turbine at low altitudes, the compressor would produce excessive manifold pressure and high operating temperatures. To alleviate this possibility, a wastegate is added to the system to control the amount of exhaust gas that is routed through the turbine. When the wastegate is open, most of the exhaust bypasses the turbine. In this situation, the engine operates much like a normally aspirated engine. When the wastegate is closed, all of the exhaust gas is used to spin the turbine. In this case, the maximum amount of compressed air is being delivered to the manifold. In some turbocharged engines, the wastegate is controlled by a pressure-sensing controller mechanism and a wastegate actuator. Once the manifold pressure is set on this type of system, the wastegate position adjusts automatically to maintain the desired power output. On less complex systems, the position of the wastegate is regulated by throttle movement. When the throttle is moved forward, the wastegate moves to the closed position. When operating this type of system, you must give close attention to throttle operations, since excessive manifold pressures can be produced at low altitudes. For specific operating procedures on the turbocharging system you're using, consult the pilot's operating handbook or aircraft flight manual. An area you need to be familiar with before operating a turbocharged engine is critical altitude. This occurs when the wastegate is completely closed and the turbine is spinning at its highest speed. Once the critical altitude is reached, manifold pressure will decrease with an increase in altitude, just like a normally aspirated engine. Another concern for turbocharged engines is the shutdown procedure. After a flight, the turbine may still be spinning at several thousand RPM. When you shut the engine down, the oil supply to the turbine is cut off. Therefore, before shutting the engine down, allow the turbine a chance to spool down with oil being supplied to it by idling the engine for the time specified by the manufacturer. When you get into a high-performance aircraft for the first time, one of the differences you'll probably notice is the propeller pitch control next to the throttle. As you will soon learn, this control is used to vary the propeller blade angle to gain additional performance and efficiency from small, lightweight aircraft engines. Before we get into the mechanics of constant speed propellers, let's quickly examine why they are more efficient than fixed pitch propellers. Thrust is a product of engine horsepower and propeller efficiency. If a propeller could operate at 100% efficiency, all of the engine's power would be converted into thrust. However, no propeller can attain 100% efficiency. Moreover, a fixed-pitch propeller produces its maximum thrust only at a specific RPM and airspeed. For example, a propeller with a low blade angle is very efficient at low air speeds, such as during takeoffs and landings, but its efficiency decreases rapidly as speed increases. Whereas a propeller with a high blade angle is more efficient at cruise speed. Fixed-pitch propellers can be designed either with low blade angles to produce optimum takeoff and climb performance, with high blade angles for optimum cruise performance and fuel economy, or as a compromise between the two. On aircraft equipped with constant speed propellers, the propeller can be adjusted to maintain the optimum pitch angle. Thus, constant speed propellers can maintain a high level of efficiency over a wide range of airspeeds. Before we get into the operational considerations of constant speed propellers, let's briefly examine the components of a typical system. These include the throttle, the propeller, or prop control, the governor, and the propeller itself. Unlike the throttle, which controls RPM on an aircraft with a fixed-pitch propeller, the throttle on an aircraft with a constant-speed propeller controls manifold pressure. The manifold pressure gauge is usually located near the tachometer and is sometimes hub houses the propeller blades, which rotate on a set of bearings, and a piston, which when pushed by oil, causes the blades to rotate to a higher pitch. When oil is released from the hub, aerodynamic forces acting on the blades of the propeller will twist the blades to a low pitch. Now that you're familiar with the components of a constant speed propeller, let's take a moment to examine how these components work to control a propeller's pitch. When you set the prop control, you're actually setting the spring tension in the governor to maintain a desired RPM. With the tension set, the system remains in a state of equilibrium until the aircraft accelerates or decelerates. When your airspeed increases, the propeller RPM considerations when using a constant speed propeller. Although engine designs vary, as a rule, you should avoid excessively high manifold pressures with low RPM settings, because high cylinder pressures can damage the engine. One way to avoid this is to always keep the prop control in the high RPM or full forward position during ground operations, takeoffs, and landings. Another way to keep from damaging the engine is to follow some basic procedures when decreasing and increasing engine power. For example, when reducing power, first decrease the manifold pressure with the throttle. Then decrease the RPMs with the propeller pitch control. It's important to note that as propeller RPM decreases, manifold pressure increases slightly. Therefore, to avoid excessive manifold pressure for a given RPM, it's best to initially reduce the manifold pressure below what is desired. Then, after the RPM is set, adjust the throttle to the desired setting. When increasing power on an aircraft with a constant speed propeller, begin by increasing the RPM, then advance the throttle. Constant speed propellers can give you better climb rates, higher cruising speeds, and extended endurance due to reduced fuel consumption. However, since the combination of manifold pressure and RPM setting needed to achieve a specific performance varies from one aircraft to another, always consult the pilot's operating handbook for the recommended power settings. So far, we have looked at how fuel injection, turbocharging, and constant speed propellers can increase engine performance. But as you extract more from the engine, it becomes more and more important that we observe the operating limitations and follow the procedures established for the aircraft by the manufacturer.
any of the systems in your aircraft, you should consult your pilot's operating handbook. Let's begin with air conditioning systems. The most common type of air conditioner found on general aviation aircraft is a vapor cycle system. These systems are very similar in operation to the systems found in an automobile or refrigerator. To activate the system, controls are provided in the cockpit. Normally, these controls include an on-off switch, a thermostat control, and a fan control. When the system is turned on, a pump compresses Freon vapor and sends it to a condenser, which is exposed to the free airstream. Here, the Freon cools and turns into a liquid. Then the Freon goes to a receiver dryer, which acts as a reservoir to ensure there is enough coolant available to meet system demand. In the receiver dryer, the Freon goes through a filter dryer. The filter removes contaminants, while the dryer contains a material that attracts and removes moisture, which could freeze in the refrigeration system and plug the line. The Freon then goes to an expansion valve where the pressure is reduced. This further cools the liquid. From there, the Freon goes to the evaporator, or heat exchanger. Here, the liquid Freon changes to a vapor. Cabin air is then passed through the evaporator. Since the cabin air temperature is warmer than the temperature of the vaporized Freon, the Freon absorbs heat from the cabin and makes it more comfortable to you and your passengers. Finally, the vapor is returned to the compressor and the cycle starts over. For winter flights or flights in colder temperatures, a cabin heater is often more essential than an air conditioner. There are two basic types of heaters: the heat exchanger and the combustion type. The first one we'll discuss is the heat exchanger, which is commonly found on single-engine airplanes. These systems pass cool ambient air through a shroud surrounding a hot component in the engine compartment, usually the exhaust system. This heats the air, which is then vented to the cabin. One danger associated with this type of system is the possibility of carbon monoxide leaking into the heating system through a defect in the exhaust system. Carbon monoxide can quickly and severely reduce your flying ability and can even cause death. If you suspect a leak or smell exhaust fumes in the cockpit, turn off the heater, open the fresh air vents or windows, and use supplemental oxygen if it's available. The other heating system is the combustion type, which is like the gas furnace in most homes. This type of heater is commonly found on multi-engine airplanes because the location of the engines make heat exchangers inefficient and impractical. This system uses a blower to force hot air from the combustion heater to the cabin. Although combustion heaters operate independent of the engines, they rely on the same fuel supply. Therefore, you should plan on increased fuel burn and decreased range when using this type of heater. If the heater overheats, an overtemp switch shuts the heater off to prevent a possible fire. In most aircraft, this overtemp switch cannot be reset from the cabin. Therefore, you'll have to continue the flight without heat, or land and reset the system. However, before flying again, make sure you've determined and corrected the malfunction. Another environmental control system commonly found on high-performance aircraft is an oxygen system. Federal aviation regulations require the use of supplemental oxygen above certain altitudes in order to compensate for the body's inability to get enough oxygen through normal respiration. There are three types of oxygen systems: continuous flow, diluter demand, and pressure demand. The first one we'll look at is the continuous flow system. This system is commonly found on general aviation aircraft and can be portable or permanently installed. Whether permanent or portable, the continuous flow system has four basic components: a high-pressure supply cylinder, a pressure regulator, a distribution system, and a continuous flow mask assembly. The oxygen supply is stored in one or more high-pressure cylinders. These cylinders must comply with strict quality standards and labeling practices. These labels identify the cylinder as containing aviators breathing oxygen, the date of the last hydrostatic test, and the highest pressure the tank can be charged to. Normally, this is 1,800 pounds. A gauge displays the pressure in the cylinder, while the on-off valve is used to start oxygen flow. On portable units, the gauge and valve are on the tank, while permanent installations often have these controls in the cabin. A pressure regulator reduces cylinder pressure to a usable level. This regulator may be manually operated or automatic. A manual regulator works the same as a water faucet. Opening the valve increases flow. The disadvantage of a manual regulator is that you must readjust it as you're changing altitude. With an automatic regulator, all you have to do is activate the system with the on-off valve. The system then compares the atmospheric pressure and cylinder pressure and adjusts the flow accordingly. In aircraft with permanent installations, oxygen outlets are located in various places throughout the cabin. Each outlet has a spring-loaded check valve to prevent oxygen leaks and allow oxygen to flow only when a mask is plugged into the outlet. The mask assembly for a continuous flow system consists of the plug-in connector with the flow restrictor, a supply hose with a flow indicator, a rebreather bag, and the mask itself. The plug-in connector has different size openings depending upon who will be using the mask. A larger opening connector is used by pilots and crew since they require more oxygen than the passengers. These connectors are usually color-coded with the passenger's supply hose marked with the gold or orange band. The pilot supply hose is marked in red. The flow indicator shows that oxygen is flowing to the mask. This device is simply a spring-loaded check valve. When the oxygen is flowing, the pressure overcomes the spring and deflects the colored valve toward the mask. The rebreather bag helps conserve the oxygen supply by mixing the oxygen with outside air. Oxygen flows continuously into the bag, causing it to expand. As you inhale, the bag collapses and outside air is drawn in through small holes in the mask. The bag is partially refilled by unused air exhaled by the user and partially by oxygen from the storage cylinder. Unused air is forced out the holes in the mask. As altitude increases, the greater flow of oxygen causes the bag and mask to be pressurized more. This results in less outside air entering the mask. In addition, the higher altitude causes the bag to expand due to the lower surrounding pressure. The continuous flow system is adequate up to 25,000 feet. Above 17,000 feet, however, you must be careful to maintain a tight seal between the mask and your face. Above 25,000 feet, you and your passengers should use some form of demand oxygen system. The diluter demand is one of these systems and is the next one we'll discuss. A diluter demand system shares the same components as a continuous flow system, except there is no rebreather bag. Instead, an additional regulator is incorporated in the mask or hose assembly. As the name implies, the diluter demand system supplies oxygen only when you inhale, and virtually all the exhaled air is forced out of the mask. As altitude increases, the regulator increases oxygen flow. Normally, you'll receive 100% oxygen by 30,000 feet, but you can select 100% oxygen at any time. The third type of oxygen system is a pressure demand system. These are more commonly installed in turboprop and jet aircraft because of their high cruise altitudes. These systems are primarily used in case the cabin pressurization system fails. At high altitudes, there is not enough atmospheric pressure to allow you to breathe normally, so oxygen is forced into your lungs. The use of pressure demand oxygen requires additional training since special techniques are required for its use. Regardless of the type of oxygen system installed in your aircraft, it's very important to have a sufficient supply of oxygen available for the planned flight. To make sure you have enough oxygen, you should use an oxygen duration graph or chart. To use this particular type of graph, you have to know how much oxygen is available and how many people will be using the system. The oxygen available is indicated in pounds per square inch of pressure on a gauge. In this example, you have 1,800 pounds in the cylinder. To find out how much oxygen is available for the pilot and 2 passengers, locate 1,800 psi on the chart, then move to the line representing the consumption rate for the pilot and 2 passengers. Next, locate the duration of oxygen available. In this case, it is slightly more than 2 hours. The pre-flight inspection should also include a check of the system itself. This can be done by turning the oxygen system on and checking each outlet for flow. Finally, brief your passengers on the use of oxygen and stress the importance of not smoking, since smoking poses a serious fire hazard. If the oxygen system fails during a flight, or if oxygen is not used for high-altitude flights, you may suffer from hypoxia. Hypoxia is caused by a lack of oxygen. Symptoms for hypoxia vary from one person to the next, but one of the first things to be affected is your judgment. Here is a list of the common symptoms. Since hypoxia impairs judgment and may not be easily recognized, it is very important to take corrective action before hypoxia develops. The FAA recommends that oxygen be used above 10,000 feet during the day and as low as 5,000 feet at night. A condition with similar symptoms to hypoxia, but from an entirely different cause, is hyperventilation. Hyperventilation is a deficiency of carbon dioxide, which causes a chemical imbalance in the bloodstream. Hyperventilation results from deep, rapid breathing, which is normally an involuntary reaction to stress, tension, anxiety, or fear. Since the symptoms of hyperventilation are similar to hypoxia, it is often best to treat the victim for both. With hypoxia, 3 or 4 deep breaths of pure oxygen should relieve the symptoms. If this doesn't work, have the individual breathe into a sac and make a deliberate effort to relax and slow the breathing rate. Talking aloud may also help. Since oxygen use may make some passengers nervous, pressurized airplanes are often more desirable. Other advantages include freedom to move around the safety release valve is installed in the cabin. If cabin pressure approaches the design limits of the airplane, this valve opens to relieve the pressure. This valve can also be connected to the landing gear safety switch so that any time the gear is down and the switch is open, the cabin depressurizes. It may also be manually opened in case a turbocharger fails and contaminated air enters the cabin. There are two types of pressurization systems, a basic system and a controllable system. All you have to do with a basic system is turn it on. When the airplane reaches a preset altitude, commonly 8,000 feet, it will begin to pressurize. As the airplane continues to climb, the cabin altitude will remain at 8,000 feet until a second preset altitude is reached. Past this point, which is commonly 20,000 feet, the cabin altitude increases as the airplane climbs. A controllable system is more complex, but it allows flexibility and control that the basic system lacks. With a controllable system, the pilot can choose where pressurization begins. For instance, you can begin pressurizing the cabin at pattern altitude, and the cabin remains at that altitude until it reaches the maximum allowable pressure differential. Then, the outflow valve maintains this pressure differential as the aircraft climbs. The outflow valve in a controllable pressurization system can also be controlled to adjust the rate at which the cabin is pressurized or depressurized. This means the airplane can descend at 2,000 feet per minute to comply with ATC instructions. But to keep the passengers comfortable, the cabin pressure can be adjusted to descend at 500 feet per minute. To increase the utility of an aircraft, it may be necessary to operate in conditions where icing is possible. While your primary goal is to avoid icing conditions, anti-ice and de-ice systems allow you to control or prevent icing to a certain degree. To legally fly in known icing conditions, an aircraft has to be certified by the FAA for that type of operation. This certification includes installation of anti-icing and de-icing systems designed to keep the airframe, propellers, and windscreen free of ice. Let's take a closer look at some of these systems. Anti-ice systems prevent ice formation, whereas de-ice systems are used to free the aircraft of ice that has already accumulated. Probably the most common anti-icing device is the pitot heater. A heater coil of high-resistance metal is built into the pitot tube housing. When the switch in the cockpit is activated, the coil's high resistance causes it to heat up and prevent the formation of ice. Many piston-powered aircraft have pneumatic airframe de-icing systems on the leading edges of wings and tail surfaces. Normally, this system consists of inflatable boots, engine-driven pressure and vacuum pumps, a timer, and pneumatic regulators. The engine-driven pressure pump inflates the boots, while the vacuum pump deflates the boots and supplies enough suction to keep the boots flat against the leading edge of the wing. The timer controls the inflation-deflation cycle. The regulator ensures the boots don't overinflate. It also may alternate the inflation and deflation of various sections of each boot to minimize the disruption of the airflow caused by the inflation of the boots. While you should follow the manufacturer's recommendations as to when to operate the system, the general procedure is to allow 1/4 to 1/2 inch of ice to accumulate before activating a pneumatic system. If the ice is too thin to break away cleanly, it may refreeze, leaving a space between the ice and the wing. Further attempts to de-ice the wing may be ineffective because the boots inflate within the cavity and don't break the ice. The second type of airframe ice control is the anti-icing system found on turboprop and jet aircraft. This system uses heated engine air routed to the leading edges of the airfoils to keep them above freezing. Heat is also used to control ice on propellers and windscreens, but heated engine air is impractical, so electrical energy is used instead. Oil and wear-resistant pads embedded with electrical heating elements are bonded to propellers. Electricity is supplied to these pads through wire brushes in the propeller hub. Since centrifugal force is sufficient to throw ice off the outboard section of the propeller, the pads usually heat only the inboard section. Some propellers are protected against the formation of ice by coating the blade surface with alcohol, usually isopropyl alcohol. With this system, alcohol is sent to a slinger ring. Injector tubes on each blade pick up the alcohol from the slinger ring and direct it to the propeller blade. Windshields may be protected with alcohol, but normally they are electrically heated. Tiny electric heating elements are laid in the windscreen or windshield panel to heat it up and melt any ice. Before flight, anti-icing chemicals may be applied to the airframe, propellers, and windshield to lessen the chance of ice adhering to these parts. Used together with anti-icing and de-icing systems, these chemicals can be very effective. Of course, flight in icing conditions may be hazardous regardless of how your aircraft is equipped. Before you enter areas of known icing, you should be sure that all of your systems are operating correctly and that you're familiar with the specific equipment installed on your aircraft. It's also a good idea to limit your exposure to icing conditions. Some of the systems described may handle ice better than others. The aircraft systems we have discussed in this section are designed to increase comfort and to allow you to adapt to an environment of reduced atmospheric pressure and oxygen levels, as well as the danger of structural icing. Thorough knowledge of the systems installed in your aircraft and good operational practices will lead to many enjoyable hours of flying.
Another system commonly found on high-performance aircraft is retractable landing gear. Retracting the gear streamlines the airplane and reduces parasite drag. This leaves more power available for better climb performance and higher cruise speeds. There are many different types of retractable landing gear, from the types found on large commercial transports to those on high-performance single-engine aircraft, with each one being identified by the power source used to extend and retract the gear. In this section, we'll look at the most common types of retractable landing gear systems: the electrical and the hydraulic. In both the electrical and hydraulic systems, you control the position of the gear by a landing gear lever located in the cockpit. By moving this lever, a signal is sent to the power source, which in turn supplies the necessary energy to raise or lower the gear. One thing you always want to do is verify you're moving the correct lever. Even though the gear and flap levers are shaped differently, a few pilots have thought they were raising the flaps, but inadvertently raised the gear. To prevent this from happening, most manufacturers have included a safety detent in the lever assembly. In order to raise or lower the gear, you must lift the lever over this detent. When transitioning to a different aircraft, make sure you're familiar with the layout of the controls. Some aircraft have the location of the gear and flap handles reversed. The first type of system we'll examine in detail is the electrical gear system. In this particular aircraft, each landing gear is mechanically linked to a gearbox, which is located in the fuselage just behind the pilot's seat. By moving the gear handle, power is supplied to an electric motor, which drives the gear toward the selected position. The motor will keep running until the up or down limit switch on the gearbox disconnects the electrical power to the landing gear motor. Should the gear fail to extend due to loss of electrical power, it can be extended by using a manual hand crank located on the floor in front of the pilot's seat. When the emergency handle is placed in the operating position, it automatically disengages the landing gear motor from the actuator box, allowing you to hand crank the gear into the down and locked position. However, because of limitations on most systems, the hand crank cannot be used to retract the gear once it is down and locked. The next system we'll look at is the hydraulic landing gear system, which uses an engine-driven pump. In most cases, the pump is located on the accessory section of the engine and uses a series of valves, pipes, and hydraulic actuating cylinders to transfer the hydraulic fluid necessary to raise and lower the gear. This system also has an emergency feature should an engine or hydraulic pump fail. Backup hydraulic pressure can be supplied by an electrically driven hydraulic pump, or in the case of some small general aviation aircraft, by a hand pump. In the unlikely event of a hydraulic leak or loss of hydraulic fluid, some aircraft have tanks of compressed air that may be used to blow the gear into the down and locked position. Another type of retractable gear is the hydraulic system, which uses an electrically driven hydraulic pump. This system is referred to as an electro-hydraulic system. Pressure in one direction raises the gear and holds it in the up position, while pressure in the opposite direction lowers the landing gear. Most hydraulic systems have an internal pressure switch, which automatically operates the hydraulic pump when system pressure falls below a specified range. This pressure is supplied to hydraulic actuator cylinders, which are attached to the gear assembly. These cylinders do the actual raising and lowering of the gear. In some systems, the gear is held up with hydraulic pressure. However, some manufacturers also use hydraulically actuated uplocks to hold the main gear in the up and locked position. In addition to hydraulic pressure, some aircraft have a heavy-duty spring attached to the gear assembly to help extend the landing gear into the down and locked position. To prevent inadvertent retraction of the gear during ground operations, most systems incorporate a mechanical squat switch located on the landing gear strut. When this switch is compressed by the weight of the aircraft, it does not allow the gear to retract. However, if the gear handle is in the up position and pressure is removed from the switch, the gear attempts to retract. This could be especially hazardous on takeoff. During normal operations, the gear should be retracted only when a positive rate of climb has been established and you can no longer land on the remaining runway. The emergency extension for an electro-hydraulic system may consist of a pressure dump valve, which relieves system pressure and allows the gear to free fall into the down and locked position. On most aircraft, a hand pump is required to supply system pressure for lowering the gear. To determine the status of the gear, indicator lights are installed. There can be one or more lights located near the gear handle. When the gear is down and locked, a green light appears. Gear in transit or in any other position besides down and locked may be indicated by an amber or red light. In most aircraft, these lights can be dimmed. This prevents them from becoming a distraction during night flights. In this example, rotating the light itself reduces the brightness. Some landing gear indicator lights have a push-to-test feature, so you can quickly determine if the bulb is burnt out. Another way to determine if a bulb is burnt out on systems with more than one light is to switch the bulb with one that is already illuminated. Most systems are set up so that all of the gear lights are interchangeable. In this way, you can quickly determine if the problem is in the lights or the gear itself. Some aircraft also incorporate a small mirror to help you visually determine if the gear is down. Another feature found on most retractable gear aircraft is a landing gear warning system. This usually consists of a warning horn that sounds when the gear is not down and locked, and the throttle is reduced below a specific point. A similar system also alerts the pilot that the gear is not down and locked when the flaps are lowered beyond a specific flap setting. The gear on some systems automatically extend when the airspeed drops below a designated value. This system also prevents the gear from retracting when below this airspeed. These auto-extension type safety features may be disarmed so the aircraft can be maneuvered with the gear up at slower speeds. For example, this system must be overridden in order to retract the gear during a maximum performance takeoff. Due to the forces imposed on the landing gear by gravity and the airstream, manufacturers have designated a couple of airspeed limitations for landing gear operations. The first is maximum landing gear operating speed, or VLO, which is the maximum speed that the gear may be safely extended or retracted. The other is maximum landing gear extended speed, VLE. This is the maximum speed you can fly with the landing gear in the down and locked position. These airspeed limitations are not shown on the airspeed indicator. However, they are listed in the pilot's operating handbook as well as placarded on the panel. Exceeding these airspeed limitations can cause structural damage to the aircraft and to critical landing gear components. During cold weather operations, slush and ice can build up on the landing gear assembly. To help prevent this from happening, try to avoid taxiing through standing water prior to takeoff. After takeoff, if there is a chance that moisture is on the gear, leave it extended slightly longer than normal to allow the air to blow it off. In this volume, we have taken a look at some of the components of high-performance aircraft, including fuel injection and how it improves the power output of your engine through better fuel distribution. Next, we looked at how constant speed propellers allow you to alter propeller blade angle to obtain optimum performance throughout a variety of airspeeds, and how turbochargers help your engine develop maximum power at altitudes well above sea level. We also learned how environmental systems can help you and your passengers remain comfortable during high-altitude flights, and how ice control can provide an additional safety margin during IFR operations. And finally, we saw how the components of different retractable landing gear systems work together to raise and lower the landing gear. Remember, each make and model of aircraft has its own distinct operating characteristics and design features. These advanced aircraft systems require you to study the pilot's operating handbook in order to thoroughly understand the different systems and take full advantage of their benefits.
In this program, we'll discuss short field operations, which are listed as maximum performance takeoffs and landings in the Commercial Pilot Practical Test Standards. We'll also look at how to perform soft field takeoffs and landings. While these maneuvers are practiced separately, there are times when you might need to combine the techniques. The first maneuver we'll discuss is the short field takeoff and climb. For training purposes, if an actual obstacle doesn't exist, you should assume there is a 50-foot obstacle at the end of the runway. Make sure your airplane has the performance to take off under the existing conditions by checking the takeoff performance charts in the airplane's POH. During your pre-takeoff check, set the flaps as recommended in the pilot's operating handbook. Before you attempt a short field takeoff, position the airplane as close to the approach end as possible and align it with the center line. Hold the brakes and apply full power before releasing them. This procedure allows you to check engine performance before starting the takeoff roll. Maintain positive directional control by using nose wheel steering until the rudder becomes effective. Allow the airplane to accelerate with the stabilator in a neutral position for minimum drag. When you reach the recommended liftoff speed, smoothly and positively rotate the airplane to an attitude which will achieve the best angle of climb airspeed, or the recommended climb speed. Maintain this speed until the obstacle is cleared. Attitude control is very important during the rotation to minimize the ground roll and maximize climb performance. If your pitch attitude is too high, induced drag becomes excessive. This significantly decreases acceleration and extends the ground roll. On the other hand, an attitude that is too low delays liftoff, which again increases the ground roll. When you're clear of the obstacle, accelerate to the best rate of climb speed and slowly retract the flaps. If you're flying an airplane equipped with retractable gear, you should raise it as soon as you have established a positive rate of climb and can no longer land on the remaining runway. Landing on a short runway, or on one which has the landing area restricted because of obstacles, requires a short field landing technique. Preparation for the landing begins on the downwind leg. There you should slow to pattern speed and extend the flaps to the first position. If your airplane is equipped with retractable gear, lower the landing gear. It's recommended that you extend the second increment of flaps while on the base leg, and full flaps when on final. All the while, progressively reduce airspeed to smoothly transition to the short field approach speed. Ideally, the final approach is conducted at a constant glide angle, airspeed, and power setting. The objective of the short field landing is to clear the obstacle, land safely, and stop the airplane with little or no floating. This requires precise control of airspeed and descent angle. Establish the approach speed early on the final approach. Normally, the recommended speed is not more than 1.3 times the power-off stalling speed. However, in gusty wind conditions, you might want to increase your airspeed to help maintain control of the airplane. Once your pitch attitude is established for the correct angle of descent, you may need only small power changes to control your airspeed. If you maintain the recommended airspeed, you'll touch down near the designated point on the runway with very little floating. After touchdown, lower the nose as soon as practical and apply maximum braking procedures. This usually includes holding back pressure on the control wheel to transfer more of the aircraft's weight to the main gear. Maintain positive directional control and follow the recommendation in the POH for flap retraction. If you touch down at the correct speed and smoothly apply maximum braking, the landing roll will be extremely short. Soft field techniques must be used when the runway surface is covered with snow, sand, tall grass, or mud. You may also want to use these same procedures to minimize the problems associated with a rough surface. If the taxiway is also soft or rough, the soft field procedure actually begins in the parking area. Plan ahead so you can keep the airplane rolling once you start taxiing. This might mean you will have to complete the pre-takeoff checks in the parking area. Once you begin to taxi, keep the airplane moving at a steady speed. You can relieve some of the weight on the nose gear by holding the control wheel in the full aft position. Before you taxi onto the runway, however, make sure the traffic pattern is clear and that all pre-takeoff checks are complete. If the approach and departure paths are clear, taxi onto the runway. When you're aligned with the middle of the runway, smoothly apply full throttle. As the engine reaches full power, check your engine instruments to verify proper operation. Continue to hold back pressure on the control wheel and maintain positive directional control. The rudder will become more effective as your speed increases. The objective of the soft field takeoff is to minimize the friction between the landing gear and the runway. To do this, you need to establish and maintain a nose-high pitch attitude as soon as possible during the takeoff roll. However, with increased speed, you have to release some of the back pressure to maintain the pitch. With the proper technique, the airplane will fly itself off the runway at an airspeed lower than the normal liftoff speed. This occurs because of ground effect. Once airborne, lower the nose slightly and accelerate in ground effect, but make sure you keep the landing gear clear of the surface. If there are obstacles in your flight path, accelerate to VX or the climb speed recommended in the POH. If obstacles aren't present, accelerate to VY. Once you've achieved a positive rate of climb and can no longer land on the remaining runway, retract the gear if appropriate. When you are clear of all obstacles, raise the flaps according to the recommendations in the POH and complete the after takeoff checklist. Now let's take a look at a soft field landing. Your objective here is to delay the transfer of weight from the wings to the landing gear until the airplane is at the slowest possible speed. The pattern and approach are normal, except you use enough power during the flare to help arrest the rate of descent. There is no need for a steep glide angle unless there are obstacles in the approach path. After you're established on final, maintain precise control of your airspeed, rate of descent, and ground track. Prior to touchdown, establish a nose-high landing attitude which allows the main gear to contact the surface with the nose wheel clear of the ground. Using power during the flare creates more airflow over the tail surfaces and helps you control the descent. The touchdown should occur just above the stalling speed. Deceleration is usually rapid on a soft surface, so the use of brakes may not be needed. In fact, the use of brakes could cause the nose wheel to dig into the surface and the aircraft to nose over. Retract the flaps as recommended. It is usually preferable to leave the flaps down during the landing roll so your attention focuses on maintaining positive directional control. You will probably need to add more power than usual as you're taxiing to the parking area. You should also maintain back pressure on the control wheel. When clear of the runway, complete the after-landing checklist. Proficiency in maximum performance takeoffs and landings allows you to safely take advantage of small and soft runways. This enables you to increase your airplane's usefulness and lets you get to areas not served by airports with long, hard-surfaced runways.
As you progress in your training, you will develop the ability to precisely control your aircraft by learning how to execute a number of maximum performance maneuvers. The steep turn develops your ability to accurately control the airplane in a maximum performance turn. You'll perform the maneuver at a constant altitude using a bank of 50 degrees. This maneuver can be performed to the left or right. As you should do when performing all training maneuvers, start by making clearing turns to ensure that the area is free of conflicting traffic. Then continue to look for traffic throughout the maneuver. Take a moment to stabilize the airplane at a constant altitude, heading, and airspeed. Begin the maneuver only after you're comfortable with the airplane's configuration. The altitude you select should allow you to complete the maneuver no lower than 1,500 feet AGL. Although any initial heading will do, you might find it helpful to start on one that is aligned with the road, section line, or other prominent landmark. The airspeed you select should not exceed the airplane's design maneuvering speed. This is very important because a steep turn substantially increases load factor. In a 50-degree constant altitude bank, the airplane is exposed to about 1.6 Gs. It's also important to monitor your airspeed throughout the maneuver, and remember that stall speed increases as bank angle increases. For example, if the stall speed is 50 knots with 0 degrees of bank, it increases to 63 knots at 50 degrees of bank. To maintain altitude with this increased load factor, you must increase lift. If you fail to do this, you will enter a spiraling descent. To prevent this, smoothly apply power and stabilator back pressure as the bank steepens, while maintaining coordinated flight with aileron and rudder. During this maneuver, you will most likely experience an overbanking tendency. This occurs because the wing on the outside of the turn is developing more lift than the wing on the inside of the turn, causing the airplane to roll beyond your desired bank. You might have to counter this overbanking tendency by applying a slight amount of aileron in the direction opposite the turn. When you reach your desired bank, confirm the accuracy of the maneuver by cross-checking the attitude indicator for proper bank, the altimeter and VSI for proper pitch, and the turn coordinator for coordinated flight. As you maintain the turn with outside visual references, you may wish to trim the airplane to eliminate the excessive control wheel pressure required to maintain altitude. If so, you must anticipate the forward pressure that will be needed during the recovery from the turn. One way to help maintain the proper pitch attitude is to select a spot on the windshield that is on a direct line between your eyes and the horizon. With a constant bank angle, you can determine proper pitch attitude by keeping the spot aligned with the horizon. Be alert for anything that might affect your altitude. For instance, if you allow the bank angle to decrease, the back pressure on the control wheel will be too great. The nose will rise, and you'll start to climb. Generally, a small increase in bank angle allows you to return to your altitude. Another situation occurs when you begin losing altitude. If you attempt to climb back to your altitude by pulling back on the control wheel, you only tighten the turn and increase the load factor. The result is a tight descending spiral, an accelerated stall, or possibly structural damage. To properly regain altitude lost during a steep turn, begin by decreasing the bank angle to reduce the load factor and allow the pitch attitude to increase. Once you've returned to your desired altitude, re-establish the bank angle and apply the proper back pressure to re-enter the maneuver. The recovery from the turn should be as smooth and precise as the rest of the maneuver. Anticipate the rollout by applying the general rule of thumb of 1/2 your bank angle. In this situation, the rollout should begin approximately 25 degrees before the recovery heading. As you roll out of the turn, the load factor imposed on the airplane is reduced quickly. This means you must decrease both back pressure and power to maintain altitude. If you use stabilator trim at the start of the turn to relieve control pressure, be prepared to exert forward pressure on the control wheel as you recover to prevent the airplane from climbing. Then retrim as necessary. While practicing the maneuver, a steep turn in one direction might be followed by one in the opposite direction. As you begin your rollout on the predetermined heading, gradually reduce back pressure until the airplane is wings level. Then begin to increase back pressure as you immediately roll into a 50-degree bank in the opposite direction. Because the nose appears lower in a right turn, you may have a tendency to gain altitude. Therefore, once you've determined that you're maintaining altitude by cross-checking the VSI and altimeter, select a new spot on the windshield to help you maintain the correct pitch attitude. Practicing steep turns will increase your confidence and ability to control the airplane smoothly. Proficiency in these maximum performance maneuvers will also improve your everyday flying skills. Another maneuver that requires a high level of planning, coordination, accuracy, and smoothness is a chandelle. The precise execution of a chandelle reveals that you have developed a thorough knowledge of how pitch, bank, airspeed, and control input must be coordinated to achieve the airplane's maximum performance capabilities. A chandelle is described as a maximum performance climbing turn with a heading change of 180 degrees. Perform the procedure with full power and smoothly increase the pitch attitude so the airspeed gradually decreases to just a few knots above the airplane's stall speed as you roll out on the recovery heading. Although obtaining maximum climb performance is an objective of a chandelle, gaining altitude is not as important as proper timing and coordination. As with steep turns, you should perform chandelles at least 1,500 feet AGL and make the necessary clearing turns prior to starting the maneuver. It's recommended that you establish yourself on a crosswind heading that will enable you to perform the chandelles into the wind. This minimizes the effect of wind drift and helps you remain in the practice area. You should also select a heading that is aligned with a prominent feature, such as a road or section line, to help you monitor your progress during the maneuver. Part of your preparation includes configuring the airplane at its maneuvering speed or the recommended entry speed. By remaining at or below this speed, you should not exceed the limit load factor. Once this is established, begin the maneuver by smoothly rolling into a 30-degree coordinated bank. Then apply control wheel back pressure to increase your pitch attitude and add full power. During the first 90 degrees of turn, you're concentrating on maintaining the initial 30 degrees of bank while gradually increasing pitch so that maximum pitch attitude is attained precisely at the 90-degree point. As you pass through the 90-degree point, concentrate on maintaining the nose-high attitude and slowly begin to roll out of the bank so that you reach a wings level attitude at the 180-degree point. When you roll out on the recovery heading, the airspeed should indicate just above stall speed. With practice, you'll learn to coordinate your rollout at a precise airspeed. Since full power is used throughout the maneuver, your airspeed is controlled by adjusting your pitch, which is the key to properly executing the chandelle. You'll find that if you increase your pitch attitude too rapidly in the turn, the airplane may stall before you complete the 180-degree turn. On the other hand, if you increase pitch too slowly, you'll have excessive airspeed at the completion of the maneuver. At the rollout point, the controls will feel mushy due to the low airflow over them, and more deflection will be needed to control the airplane. You'll also experience the left-turning tendencies produced by P-factor and spiraling slipstream. As with any phase of flight, control the adverse yaw by referring to the turn coordinator and keeping the ball centered. Hold the rollout heading momentarily and then smoothly recover by slowly lowering the nose to a level flight attitude. Your objective is to allow the airplane to accelerate back to cruise airspeed while maintaining a constant altitude. Practicing chandelles will help you learn positive control techniques at varying airspeeds and attitudes, which will improve your ability to control your airplane during maximum performance maneuvers. As you continue practicing commercial maneuvers, you'll be introduced to advanced figure 8 procedures. Let's take a look at a maximum performance maneuver called a lazy 8. Because the procedure incorporates various combinations of climbs, descents, and turns, you must have a complete understanding of the airplane's performance capabilities. In addition, the maneuver will help you develop and improve your coordination, division of attention, and ability to precisely control the airplane. Basically, you'll perform two 180-degree turns in opposite directions. Each turn contains a climb and a descent to return to your entry altitude and airspeed. The Lazy 8 should be flown just as its name implies, in a smooth, gentle manner. Before beginning, establish yourself at an altitude that allows you to complete the entire maneuver at least 1,500 feet above the ground, and determine the wind direction so you can start the Lazy 8 on a crosswind heading. Plan to make the turns into the wind so you won't drift from the practice area. This will also help you maintain symmetrical loops. As you do when practicing all maneuvers, clear the area before you begin. Then remain vigilant for traffic throughout the maneuver. Begin the maneuver by aligning the airplane on the entry heading. Then, to help maintain orientation, select a 90-degree reference point. This point should be on the horizon and abeam your flight path. Additional reference points at 45 degrees, 135 degrees, and 180 degrees are also helpful. Start in straight and level flight at a normal cruise power setting and at the recommended airspeed. Since the power setting does not change during this maneuver, pitch attitude controls airspeed. When abeam the 90-degree reference point, begin the maneuver. During the first 45 degrees, concentrate on performing a gradual climbing turn toward your reference point. At the 45-degree point, you should reach your greatest nose-high pitch attitude. The bank angle should be approximately 15 degrees and increasing. Since your airspeed decreases during the climb, maintain coordinated flight by using enough right rudder to counteract torque. Throughout the second 45 degrees of turn, continue to increase your bank and smoothly lower the nose. Your objective is to pass through the 90-degree point in a level pitch attitude and at the maximum bank angle, which is approximately 30 degrees. At this point, you should also be at the maximum altitude and minimum airspeed. This speed for most general aviation training aircraft is slightly above the stall speed. As you pass through the 90-degree point, gradually lower the airplane's nose and slowly decrease the bank angle. Your goal is to reach the 135-degree point at the greatest nose-low pitch attitude. The bank angle should be approximately 15 degrees and decreasing. As the airspeed continues to increase, maintain coordinated flight and time your rate of rollout and pitch change so you reach straight and level flight at the 180-degree point. This should be abeam the 90-degree reference point at your entry altitude and airspeed. Immediately enter a climbing turn in the opposite direction. Complete each 45-degree segment in the same manner as it was performed during the first half of the maneuver. As you practice Lazy 8s, you'll develop the timing and coordination needed to achieve the proper pitch and bank adjustments. For instance, you'll find that if you apply insufficient nose-high pitch during the climbing turn, you might reach the 90-degree point with excessive airspeed. On the other hand, increasing pitch too rapidly could cause you to gain too much altitude, lose too much airspeed, and possibly stall the airplane. Another possibility is to improperly reduce bank during a descending portion of the maneuver. This will cause you to overshoot or undershoot your rollout heading. Just remember, the control pressures during a Lazy 8 should be gradual and smooth, resulting in a slow, gentle, coordinated procedure. Another ground reference procedure that involves flying in a figure 8 pattern around 2 points on the ground is the 8s on pylons. During 8s on pylons, you don't maintain a uniform radius around the pylons, nor do you try to maintain a constant altitude. Instead, your goal is to vary your altitude and airspeed to keep a reference point, usually located near the wingtip, on the pylons. This reference point varies depending on your sitting height and position and the wing design of your airplane. Regardless of its exact position, the key to selecting the reference point is that your line of sight through the point must parallel the airplane's lateral axis. When performing 8s on pylons, you should maintain the reference point on the pylon so the airplane appears to pivot about it. The altitude that enables you to do this is called the pivotal altitude, and it is governed by your ground speed. As your ground speed increases, the pivotal altitude increases. Likewise, a decrease in ground speed causes your pivotal altitude to decrease. With all of this in mind, let's look at the planning and coordination needed to fly 8s on pylons. After clearing for traffic, start by determining the wind direction, and then select 2 pylons that are in an open area free of hills and obstructions. They should be spread far enough apart to permit a few seconds of straight and level flight as you fly between them. The pylons should be aligned perpendicular to the wind, and at approximately the same elevation to make altitude adjustments easier to accomplish. Plan to enter the maneuver near the pivotal altitude, which you can estimate by using this simple formula. First, approximate your true airspeed in miles per hour and square this value. Then, divide the product by 15. For example, if your true airspeed is 110 miles per hour, your approximate pivotal altitude is 807 feet AGL. You can also use the same formula with knots, but in this case, you will need to divide by 11.3. Since you seldom know your exact true airspeed, you'll need to find the desired altitude by experimenting as you fly the procedure. After you adjust power for the recommended entry speed, enter the maneuver by flying diagonally between the pylons. When you're approximately abeam the first pylon, roll into the turn. At this point, your ground speed is highest, which means you're at the highest pivotal altitude. As you continue the turn into the wind, your ground speed gradually decreases. If you fail to adjust for the reduced ground speed, the reference point moves behind the pylon. This means you're too high. To bring the reference point back to the pylon, lower the nose to descend to the pivotal altitude. As you proceed around the first pylon, your ground speed increases, so gradually raise the nose to keep the reference point aligned with the pylon. If you don't initiate the climb, the reference point moves ahead of the pylon. This means you're below the pivotal altitude. Remember, increased ground speed means an increase in the pivotal altitude. In addition, since a constant radius is not a requirement for this maneuver, you should not correct for any drifting. Therefore, use varying bank angle to keep the reference point on the pylon. The closer you are to the pylon, the steeper the bank. When the first turn is completed, roll out into straight and level flight for 3 to 5 seconds as you fly toward the second pylon. During this portion of the maneuver, you'll need to crab into the wind to correct for drift. Once you're abeam the next pylon, begin a turn in the opposite direction. As you continue the maneuver into the wind, ground speed decreases. Therefore, gently allow the airplane to descend to keep the wingtip reference aligned on the pylon. Correct for any deviations from your desired reference by gradually and smoothly adjusting your pitch attitude. During the final portion of the turn, your ground speed once again begins to increase. Thus, your pivotal altitude must subsequently increase to maintain the proper alignment. Continue the turn until you roll back to straight and level flight between the two pylons. The key to successfully flying 8s on pylons is to hold the reference point on the pylon by changing your altitude, rather than using uncoordinated rudder pressure. Coordinated flight should be maintained throughout the entire Figure 8 maneuvers. Commercial flight maneuvers are designed to help you attain a high level of competency in controlling the airplane. As you increase your ability to precisely execute them, you'll also increase your understanding of the airplane's maximum performance capabilities as well as its limitations.
In this program, we'll look at the steep spiral, which is another maneuver that emphasizes planning, coordination, orientation, and aircraft control. Although the steep spiral is primarily a training exercise, it can be useful in some emergency situations. A steep spiral is basically a gliding descent using no more than 50 to 55 degrees of bank where you maintain a uniform radius around a reference point. The maneuver can be performed either to the left or right. Typically, you'll enter the procedure, complete 3 360-degree turns, then roll out on your entry heading. Let's look at how you perform the steep spiral. Your initial planning includes establishing the airplane at a height that will enable you to perform the procedure and recover at a safe altitude. After you've determined the location where you wish to perform the maneuver, clear the area by carefully looking for traffic below as well as in your general vicinity. To maintain orientation, you need to select a good ground reference point. The intersections of roads or fields are easily seen from the air. You should also select a prominent landmark near your entry heading. To aid you in rolling out of the maneuver, it's also a good idea to check your heading. Before starting the maneuver, stabilize the airplane at the recommended entry speed. This is the airspeed you should maintain throughout the procedure. Although any entry heading will do, you should try to enter the maneuver downwind. By doing this, you will use the steepest bank angle at the beginning of the maneuver. This then assures you that you'll be able to make the necessary adjustments in order to maintain a uniform radius. When you're ready to begin, apply carburetor heat if required and smoothly close the throttle. As you roll into the turn, you will probably have to lower the nose of the airplane to maintain airspeed. Use a reference spot on the windshield to maintain the correct attitude and periodically cross-check your airspeed. Remember, if the turn is to the right, you'll need to use a different reference point. When you first begin practicing steep spirals, you might find that using shallower bank angles and a larger radius of turn will help you become more comfortable with bank and airspeed control. Since one of the objectives of the maneuver is to maintain a constant radius about the selected reference point, you must adjust the bank to correct for any wind drift and changes in the ground speed. As you discovered while performing S-turns and turns about a point, ground speed and bank angle are directly related. The faster your ground speed, the steeper the bank needed to maintain a constant radius. Therefore, airspeed control is a critical factor in performing the maneuver. The faster your airspeed, the greater the ground speed and radius of turn. Since you're at idle power during this maneuver, you'll have to maintain airspeed by adjusting the pitch attitude. Periodically add power to clear the engine as you continue through the maneuver. This helps prevent excessive engine cooling and spark plug fouling caused by prolonged operation at idle power. To minimize ground speed variations, it's helpful to do this while heading into the wind. When you perform any maneuver in which high bank angles are used, it's important to maintain an awareness of the load factors imposed on the airplane. Any improper use of the controls can abruptly increase the load factor, which can lead to an accelerated stall or structural damage. In addition, pulling back on the control wheel to reduce excessive airspeed may actually tighten the spiral. The proper procedure to correct for excessive airspeed is to decrease bank angle, then apply back pressure. To recover from a steep spiral, use your heading indicator and the standard 1/2 of the bank angle, along with your chosen landmark to determine when to begin a smooth rollout. As you level the wings, smoothly adjust pitch to maintain your airspeed and continue a glide on the recovery heading. During practice, be careful not to descend below a safe altitude. One practical application of the steep spiral is during an emergency landing. If you lose power and have sufficient altitude, you can glide directly to your point of intended landing and then lose altitude by performing a steep spiral until you roll out on the downwind leg. As you're descending, you can inspect the site for obstructions or hazards. You can also determine the approximate wind direction and velocity. Adjust the spiral to roll out on a downwind heading as though you were going to make a normal approach at an airport. During an actual forced landing, you would continue to maintain your desired airspeed and plan on arriving at the key position with enough altitude so that you can land into the wind. The steep spiral is an excellent training maneuver because it helps you develop the ability to accurately control the airplane. In addition, it gives you a way to safely descend to the landing site should an actual emergency occur.
Let's look at another maneuver, the power-off 180-degree accuracy approach and landing. It's an approach to land with the engine at idle that uses only the glide angle under prevailing wind conditions to fly a specific pattern and land on the runway at a predetermined point. Power-off accuracy approaches and landings are designed to develop your ability to judge gliding distance and to control descent angle during a power-off approach to a safe landing. By understanding the power-off characteristics of your aircraft, you can improve your skills in estimating glide distance and in judging the effects of wind. The approach begins on the downwind leg with the aircraft at pattern altitude, typically no higher than 1,000 feet AGL. Make your normal pre-landing checks, including the extension of the landing gear if necessary. While on downwind, select your point of intended landing. Once you reach the downwind key position, which is opposite the point of landing, reduce the power to idle, adjust the pitch to maintain altitude, and decrease airspeed to the manufacturer's recommended power-off glide speed, or, if no speed is given, 1.4 VSO. Then lower the nose to maintain that airspeed. Your turn to the base leg of the pattern is governed by the existing wind conditions and glide angle. Stronger winds require a turn to base sooner than if lighter wind conditions prevail. Also, take into consideration the fact that strong headwinds affect your final approach as well. Use the turn to base leg to dissipate or conserve altitude as necessary to meet your intended landing position. Once you arrive at the base leg key position, which is 45 degrees from the intended landing position, lower your flaps as necessary and retrim the aircraft to maintain best glide speed. The turn to final is timed so your rollout is aligned with the center line of the runway. Your goal on final approach is to descend at an angle that allows you to reach the intended landing position at an airspeed that results in little or no float just prior to touchdown. Remember, in a power-off situation, the pitch attitude controls the airspeed, which in turn controls the glide of the aircraft. Lower the flaps as necessary and make small adjustments to the pitch attitude to control your glide angle and airspeed. While your goal is to touch down within 200 feet of the point on the runway, but not before it, with little float, do not attempt to stretch the glide or retract the flaps in order to make the landing point. Concentrate on making a safe landing, then re-evaluate your downwind and base locations and flap positions for the next power-off approach attempt. Take time to evaluate your aircraft's performance in various wind conditions and with a variety of flap settings. Doing so enhances your ability to judge altitude, glide angle, and distance. If you can accurately estimate your glide angle and its resulting distance, you can judge how much maneuvering is possible to safely reach a given spot on the ground